So here we've got the Casio fx-CG100 graphing calculator, and let's open it up. So when we open it up, we've got ourselves some batteries, and if we open up the box, we've got various different leaflets, as we see here, manuals, etc. And here we've got the actual calculator. So let's open this up. What we can see beautifully engraved is my name. It's got a nice feel to it. So let's open this up. As follows, we've got the protective covering on. Here's where we put the batteries in. And of course we've got the case over here. So let's insert the battery and get started with our calculator. The layout of the calculator is as follows. On the top we have the screen, and elsewhere we have various different keys. For example, here we have the number keys. Here we have the operation keys, etc. Furthermore, we have the home key, and pressing the home key will display the main menu. We have the settings key. We have these arrows, which are used for navigation. We have the return key. We have the OK key. Just as an extra note, the OK key and the execute key perform the same function. When we put the batteries in, we've got this screen which appears. So this will essentially allow us to set up the calculator for its first use. So let's let the language to be English. Let's confirm. Let's change the country settings to be United Kingdom, and then confirm. We can adjust the brightness of the screen. We can make it dimmer, we can make it lighter. Let's use this setting. We can change the power properties, so we can have the calculator turn off automatically after 10 minutes. We can change the backlight settings. I'm going to change that to be 1 minute. Let's confirm this. I've put in alkaline batteries. The second option is for rechargeable batteries. We've got alkaline batteries. This pop-up appears which tells us that the battery capacity detection depends on the battery type. Let's confirm this. And here you can see our calculator is set up. To turn on the calculator, we would simply press the on button. As shown, the calculator has been turned on. Now, to turn off the calculator, you see off is over here, so you press shift, then the AC button. This turns off the calculator. From the main menu, you will notice we have various different sub-menus or applications. We can navigate through these using the arrow keys, as shown here. When a particular application is highlighted in black, as we see here, that indicates the position is currently at calculate. If I scroll to the right, the position now is at statistics. Scrolling down, the position is at dynamic graph. Scrolling to the left, the position is now at graph and table, and scrolling back up, the position is now at calculate. We can scroll down further by pressing the keys here. And to return the position to calculate, we would press the home key once again. Once we are at a particular position, we can access that sub-menu by pressing OK. So for example here, if we were to enter into the Calculate sub-menu, we can press OK. To return to the main menu, we press the Home key. You will also notice the different applications have numbers or letters assigned to them. For example, the 3D graph application has a number 8 assigned to it. We can access that directly by pressing the 8 key. Here we are now in the 3D graph application. Let's return to the main menu by pressing Home. As another example, if we wish to enter into the equation sub-menu, we can press A. Now, there is no direct button for A, but you will notice A is to the top right of this key. So if I press this key, this will allow us to enter into the equation sub-menu, as shown. Let's return to the main menu by pressing Home. Now, one thing we can do, if we go to the settings, and if we scroll down to username, we can enter in our name and organization. So let's input my name. I've got TAYYUB, and then we've got my surname, which is MAJEED, and the organization, we've got TM Maths. So let's go back. What's the effect of this? Well, if I turn off the calculator, we can see that appear in the bottom right of the screen. To reset your calculator, from the main menu, scroll down to the System sub-menu. Press OK to enter into the System sub-menu. Highlighted for us is the Resetting option. So if I press OK and then scroll down to Main and Storage, this will clear the main memory and the storage memory. So if I press OK, I'm pressing number 1, and then pressing number 1 again will allow us to clear the main memory and the storage memory. One thing we can do with our calculator is connect it to a computer. Now, you'd find here on our calculator we got a USB-C. So, with our USB-C cable, let's plug that in from this end, as we see here, and let's plug in the other bit into our computer. So once we have plugged it in, what it says is we can either press the first option for USB flash or we can update it. Let's press the first option for USB flash and then press OK. It prepares the USB, and then what we can do is open this up, and you've probably seen the pop-ups appear on the bottom right of the screen. So you can see here, we can open this up. We can explore through the various different files within our calculator. And what you'll see appearing on our screen is a caution message, and we also see tips appearing on our calculator. Now, of course, we have to terminate the USB connection on our computer before we take out the USB, just for safe measure. So what that means is we right-click here, let's eject safely, and then we've got to unplug now. Let's explore how to enter into the exam mode. Now, if we scroll to the exam mode and then press OK, we can enter into the exam mode. as shown. Now before that, if we go to the third option for exam mode help, that tells us, at least in the United Kingdom setting, what applications we cannot use. It also gives us instructions on how we can exit. So now let's enter in exam mode. Let's press OK. Let's press OK for the United Kingdom settings, and if I press OK, this warning pop-up appears, and what it says is, this examination mode is not allowed for the International Baccalaureate qualifications. So let's press OK on that. It's entering into the examination mode. You see it loading, and if we zoom into the screen as shown here, what you can see is we've got this border which will show that we are in examination mode, and scrolling through you can see some applications have been restricted, such as the database, Python has been disabled, the probability simulator has been disabled, the probability simulator has been disabled, as well as the memory. We can exit examination mode as follows. One way we can exit is to wait 12 hours, and if we wait 12 hours, that will automatically exit out of examination mode. But we can also exit out of examination mode as follows. What we can do is connect our calculator to the computer using the USB cable as follows, and then we would select the first option for USB flash, and then it also gives us an option to unlock examination mode. Now once our computer is loaded up the calculator, let's go into this main menu, and then we can paste in any file such as an image, as we see here. So now what we need to do is exit out of this and safely unplug our calculator. So let's right click here, let's eject, let's close that up, and let's take this out, and in the meantime what you can see is the calculator is loading again, and we are now unlocked out of examination mode. Let's change the country settings on our calculator. If we go to the settings and then the fourth option where we can change the country settings, currently we are set at international. Let's change that to United Kingdom. And if we go back to the home screen, what happens is the applications appear in a different order. So now we have the first option being calculate, the second option being equation, and so on and so forth. Let's change that back to international to show that. So let's go back to the settings, the fourth option for country. If we change this back to international, we've got calculate, then statistics rather than equation. It also makes a difference when we select exam mode as well. So ensure that your calculator has the correct country selected. From the calculate sub menu, you will find we have different tabs, and we can scroll through those different tabs using this key and this key. Currently, we are using the calculation tab. If I press this key, we are now at the vector tab, and if I press this key again, we are now at the matrix tab. And if I press this key once again, we end up back at the calculation tab. You will notice we have silver functions and gold functions. The silver functions are to the left of a key and gold functions are to the right of a key. So for example, if I take a look at the 7 key, to the left of it we have pi, which is a silver function, and to the right of it we have m, which is a gold function. To access the silver function, we begin by pressing shift, and when we press shift you will notice the up arrow appearing. We then press the relevant key. So for example, to access the pi function, once we've pressed shift, we then press the 7 key. Here you can see the pi function. To access the gold function, we would begin by pressing alpha, and when we press alpha you will notice the A appears here. And if we wish to select the M function, we then press 7 after having pressed alpha, and in doing so you can see the M function being selected. To execute a calculation such as 5 multiplied by 9, we press execute. 5 multiplied by 9 is equal to 45. Let's suppose we are working with various different calculations. So for example, 9 multiplied by 3, which is 27, 8 squared, which is 64, 25 subtract 14, which is 11, 76 divided by 2, which is 38. You can see we have worked out various different calculations. If we want to delete a particular calculation, for example, I want to delete the calculation 25 subtract 14, we click the 3 dots here for the tools function, and then we scroll down to number 2 to delete this line, and if I press OK and then OK again, you can see that line has been deleted. Let's suppose I want to clear all of my calculation screens. Then in this case, pressing tools, we can scroll down to number 3 to delete all, and if I press OK and OK again, the entire calculation screen has been cleared. Suppose we have the number 3.5. If I execute, our calculator displays for us 3.5. If we press the format key, that will rewrite 3.5 as 7 over 2. If we press shift and then the format key, we have other ways in which we can write 3.5. So for example, selecting the second option, 3.5 can be rewritten as 3.5. Let's suppose we want to work out 153 divided by 6. The answer to this is 25.5. Now, let's now suppose we want to use this answer, and with this answer, add on 4. So, you can see answer is a gold function, so we press alpha, then the format button. This has stored into it 25.5. We want to add to this 4. If I then execute, you can see the answer is 29.5. You have to use the formula xn plus 1 equals square root of 5 plus xn, with x0 equaling 1 to find an approximate solution to the equation x squared subtract x subtract 5 equals 0. Now, to do this, we will utilize the answer function. To begin with, let's key in 1 and press execute. So far, 1 is stored into the answer function. So now, using the iterative formula, we have the square root of 5 plus answer. Of course, we've replaced xn with the answer function. So, if we press execute and convert to a decimal, x1 is equal to 2.449, etc. If I press execute once again, x2 is equal to 2.729, etc. If I press execute again, x3 is equal to 2.780, etc. If I press execute again, x4 is equal to 2.789, etc. If I press execute again, x5 is equal to 2.790, etc. If I press execute again, x6 is equal to 2.791, etc. If I press execute again, x7 is equal to 2.791, etc. And we can continue on up until we get convergence. And eventually, what you will see is x is equal to 2.791,287,847. We can use our calculator to store and recall values. Now, you will notice we have these gold functions a, b, c, d, etc. These are variables in which we can store certain values into. Now, let's take a look at an example as to how we store. Let's suppose we work out 89 multiplied by 6. The answer to this is 534. Now let's suppose we want to store this 534 into the variable p. You will notice we have the right arrow over here. This is the store function, and it is a civil function. So we press shift followed by this key. This now prompts us to store this answer into a particular variable. We want to store this into variable p. So we press the alpha key followed by the 4 key. This means this answer will be stored into p. Let's execute. P is now assigned with a value of 534. Now let's suppose we have another calculation. 25 plus 37. The answer to this is 62. Let's suppose we want to store 62 into the variable q. So we press Shift followed by this key. We want to store into Q, so press Alpha followed by the 5 key, and then press Execute. Q has a value of 62 assigned to it. If we now wish to use the variables P and Q in calculations, then quite simply we can recall those values. So for example, let's suppose we want to work out 3P plus 2Q. Well, we have 3P plus 2Q, and you will find this to equal 1726. Now, if I press the variable key as shown here, the first option, alpha, will tell us what the variables have values of. So if I press OK, you can see A, B, C, D, etc. all currently have values of 0. And if I scroll down, you can see currently we've got an answer of 1726 in the answer function. And you can see for P and Q, we've got values of 534 and 62 respectively. Let's suppose we worked out 6 squared plus 47. If we execute, we end up with 83. Now let's suppose we want to use this 83 and subtract from it 9. Using the answer function, we press Shift, then Format, and then we subtract from this 9. You can see the answer is 74. But let's suppose we realized an error. Instead of adding 47 to 6 squared, let's suppose we wanted to add 43 to 6 squared. If we use the arrows to navigate back to this, you can see the cursor is to the right of 47. If I use the key here to delete the 47 and instead put 43, if I then execute, you can see 6 squared plus 43 is 79, and then 79 was used in our calculation. We then subtracted from that 9 to get 70. Often we'd use brackets in calculations. Now here and here we have bracket keys. Let's suppose we have in a bracket 3 multiplied by 6, subtract 2, close the bracket, and we wish to square this result. You will notice the 3 multiplied by 6 subtract 2 is enclosed in blue brackets. This means whatever is in between the blue brackets is calculated. That result is then squared. This is using the principles of order of operation. So if we execute, of course we get 256. Now let's suppose we open up our bracket. It opens up in the blue colour. And now let's key in 25 multiplied by 9 divided by, and if I now open up another set of brackets, 3 plus 2, then close those brackets, and then from this subtract 7, and then close the brackets, and then cube the result. Here you can see we have an inner bracket and an outer bracket. For the inner bracket, that's in red. For the outer bracket, that's in blue. So, the calculator would calculate for us what goes in this bracket. So 3 plus 2, that's 5. And then instead of us having a 3 plus 2, it would do 25 multiplied by 9 divided by 5, subtract 7, and then the result will be cubed. The point of this exercise is to demonstrate when we have multiple brackets, the colours of those brackets change accordingly. If we execute this result, we end up with 54,872. We can use our calculator to manipulate fractions. Here is the fraction key. Pressing it, we have the numerator and the denominator. Let's suppose we have the fraction 10 over 4. If I press execute, the calculator displays for us 10 over 4 as a fraction in its simplest form. To find the decimal equivalent, we press format. You can see 10 over 4 is equal to 2.5. Now let's suppose we want to write 10 over 4 as a mixed number in its simplest form. To do this, we have Shift, then Format, and then if I scroll to number 2, we can switch between a mixed number and a top-heavy fraction. You can see 10 over 4 is the same as 2.5. We can use our calculator to manipulate mixed numbers. Mixed numbers are a silver function on your calculator, and to access this, press Shift, then the fraction key. Let's suppose we have 5 and 2/3. If we press execute, our calculator displays for us the top heavy fraction 17 over 3, which is equal to 5 and 2/3. Here is the square root key. Pressing it, we can now input the square root of something, such as the square root of 81. Pressing execute, we find that to equal 9. We have to write in its simplest form the square root of 20. If we key in the square root of 20 and then press execute, you will find the square root of 20 to equal 2 root 5. We have to write in its simplest form 20 subtract root 50 over 3 root 2 subtract 5. Let's key this in. We press the fraction key. For the numerator, we have 20 subtract root 50. For the denominator, we have 3 root 2 subtract 5. And if we press execute, you will find the result to equal negative 10 subtract 5 root 2. We can use our calculator to work out the nth root of a number. Let's suppose we want to work out the 5th root of 32. The nth root function is a silver function, so we press Shift, then the square root symbol. We want to work out the 5th root of 32, and if we execute, you will find the fifth root of 32 to equal 2. We can use our calculator to square something. The squared key is here. Let's suppose we work out 5 squared. 5 squared is equal to 25. We can further manipulate with the squared button. For example, if we have 3 root 2 subtract 1 and we wish to square this, you will notice brackets appear in blue. Pressing the squared key, we have 3 root 2 subtract 1 squared, and executing, you will find 3 root 2 subtract 1 squared is equal to 19 subtract 6 root 2. We can work out the nth power of something using this key here. Suppose we want to work out 4 to the power of 5. We have 4, and press this key, and then key in 5. 4 to the power of 5, that's equal to 1024. E has its own dedicated key here. If we press E, automatically we have to enter in a power. To find the value of E, we have e to the power of 1, and if I execute this, we end up with 2.718, etc. As another example, we could have e to the power of -1, which is the same as 1 over e, and that's equal to 0.367, etc. We can use our calculator to work with logarithms. You will find on your calculator we have log base a of b, the log of a, and the natural logarithm. These are all silver functions, which means to access them we would have to press Shift followed by the key we desire for the appropriate logarithm. Let's suppose we want to work out log base 2 of 8. Press Shift and then this key. We have log base 2 of 8, which is equal to 3. Let's suppose we want to work out log of 100, which is the same as log base 10 of 100. Press Shift and then this key. We have log of 100, which is equal to 2. Let's suppose we want to work out the natural log of e. Press Shift and then this key. We have the natural log of e, and of course e is the same as e to the power of 1. The natural log of e is equal to 1. Pi is a silver function. We can key this in by pressing Shift, then 7. And then if I press Execute, we have pi. We can find the decimal equivalent by pressing Format. You see pi is equal to 3.141, etc. We can use our calculator to work with trigonometric functions. We have the key for sin x, the key for cosine x, the key for the tangent of x. As an example, if we were to work out the sine of pi over 2, well, we have the sine of pi over 2, which is equal to 1. If we were to work out the cosine of negative pi, the cosine of negative pi is equal to negative 1. If we were to work out the tangent of 7 pi over 4, the tangent of 7 pi over 4 is equal to negative 1. We can use our calculator to work with the inverse trigonometric functions. Those are the inverse of sine, the inverse of cosine, and the inverse of tangent. And you'll notice those functions are silver functions, meaning to access them, we would have to use shift followed by the sine key to use the inverse sine function, shift followed by the cosine key to use the inverse cosine function, and shift followed by the tangent key to use the inverse tangent function. As an example, if we were to work out the inverse sine of 1, we press shift followed by sine and then 1. The inverse sine of 1 is equal to pi over 2. If we were to work out the inverse cosine of 1/2, you press shift followed by the cosine key, and then we have 1/2. It turns out we end up with pi over 3. And if we were to work out the inverse tangent of 1, press shift and then the tangent key. The inverse tangent of 1 is pi over 4. We can change the angle units using our calculator. To do so, press settings, and if we go to the angle setting and press OK, you can see a tick appears to what we have currently. Currently, the angle unit is set to radians, and you can see that here. We can change this to degrees by pressing number 1. You can see we now have degrees. Let's work with this. Suppose we have the sine of 30 degrees. If we execute this, we end up with 1/2. Let's go back to radians. Press settings, change the angle unit to radians. Let's suppose we have the cosine of pi. You will find this to equal negative 1. Another useful feature, if we are in radians, we can still calculate in degrees. Let's suppose we want to work out the tangent of 45 degrees. If I press the tan key and then 45, we don't have our calculator set in degrees so far. However, if we press the catalog key and then scroll down to angle coordinate sexagesimal, and then press number 1 for degrees, the tangent of 45 degrees is equal to 1. Let's switch our calculator back to degrees. Press Settings. The angle unit we wish to use now is degrees. Let's suppose now we want to work out the cosine of pi over 2. The cosine of pi over 2, well, currently we are in degrees. We want the pi over 2 to be in radians. If I press the catalog key, scroll as we did previously, we want radians. The cosine of pi over 2 radians is equal to 0. We can use our calculator to work with hyperbolic functions. If we press the catalog key, and if we scroll down to number 8, where we have hyperbolic calculations, and then press OK, you can see we have hyperbolic sine, hyperbolic cosine, hyperbolic tangent, the inverse hyperbolic sine, the inverse hyperbolic cosine, the inverse hyperbolic tangent. Let's demonstrate the use of these through examples. Let's suppose we want to work out the hyperbolic sine of 2.2. Press the catalog key, scroll down to hyperbolic calculations, and then press OK. Press OK for hyperbolic sine. We have hyperbolic sine of 2.2, and if we execute, you will find this to equal 4.457, etc. Let's suppose we want to work out the hyperbolic cosine of negative 0.5. If we press the catalog key, scroll down to hyperbolic calculations, press OK, scroll down to hyperbolic cosine, and then press OK. We want to work out the hyperbolic cosine of negative 0.5, and you will find this to equal 1.127, etc. Let's suppose we want to work out the hyperbolic tangent of 0.6. If we press the catalog key, scroll down to hyperbolic calculation, and then press OK. Scroll down to hyperbolic tangent, and then press OK. We want to work out the hyperbolic tangent of 0.6, and you will find this to equal 0.537, etc. Let's suppose we want to work out the inverse hyperbolic sine of 0.75. If we press the catalog key, scroll down to hyperbolic calculation, and then press OK. Scroll down to the inverse hyperbolic sine function, and then press OK. We want to work out the inverse hyperbolic sine of 0.75. You will find this to equal 0.693, etc. Let's suppose we want to work out the inverse hyperbolic cosine of 2. If we press the catalog key and scroll down to Hyperbolic calculation and then press OK. And if we scroll down to the inverse hyperbolic cosine function and then press OK, we want to work out the inverse hyperbolic cosine of 2. And what you will find this to equal is 1.316, etc. Let's suppose you want to work out the inverse hyperbolic tangent of 0.8. If we press the catalog key and scroll down to hyperbolic calculation and then press OK, and if we scroll down to the inverse hyperbolic tangent function and then press OK, we want to work out the inverse hyperbolic tangent of 0.8. And what you will find this to equal is 1.098, etc. We can use the CG50 to write numbers as the product of their prime factors. Let's suppose we want to write 45 as the product of its prime factors. If I key in 45 and then press execute, then press tools, and then scroll down to number 4 where we have prime factorization and then press OK, this pop-up appears which tells us 45 is equal to 3 squared multiplied by 5. We can use our calculator to work out the highest common factor of two numbers. Suppose we want to work out the highest common factor of 12 and 18. We begin by pressing the catalog key, scroll down to numeric calculation and then press OK. Press number 1 for GCD, which stands for greatest common divisor, or in other words, highest common factor. We want the highest common factor of 12 and 18, and if we execute, we will find the highest common factor of 12 and 18 is 6. We can use our calculator to find the lowest common multiple of two numbers. Let's suppose we want to find the lowest common multiple of 16 and 24. If we press the catalog key and then scroll down to numeric calculation and then scroll down to LCM, which stands for lowest common multiple, and then press OK, we want the lowest common multiple of 16 and 24. And if we work this out, we get 48. The lowest common multiple of 16 and 24 is 48. We can use our calculator to work with factorials. For example, if we wish to work out 6 factorial, well, we have the 6 key, and then to access factorial, press the catalog key, we scroll down to probability, and then the first option is for factorial. 6 factorial, that's equal to 720. We can use our calculator to use the NCR function. Suppose we want to work out 5 choose 3. We have 5, and to access the choose function, press the catalog key, scroll down to probability, and scroll down to the third option where we have combination. 5 choose 3, that's equal to 10. We can use the absolute value function on our calculator to find the modulus of a number. Now let's suppose we want to find the absolute value of -5. In other words, we want to find the modulus of -5. If we press the catalog key and then scroll down to numeric calculation and then press OK, and then press number 1 for absolute value, we want to find the absolute value of -5, which is 5. We can use our calculator to work with summations. To access this, press the catalog key, scroll down to function analysis and then press OK, and then scroll down to summation and then press OK. You see the following on the screen. So for example, we can work out the sum of 3x subtract 2 from x equals 4 to x equals 7. And working this out, we get 58. We can use our calculator to work with numbers that are written in standard form. Here is the key for numbers written in standard form. We have the times 10 to the n button. So for example, if we have 5.6 times 10 to the 3, and if I execute this calculation, we have 5,600. The calculator allows you to convert between units. We can convert units by accessing the catalog, and we press this key here. And if we scroll down, we can convert units using option C. We can convert lengths, areas, volume, time, temperature, velocity, mass, force, pressure, energy, and power. Suppose we want to convert 5 meters into centimeters. We begin by pressing the 5 key, then the catalog key. We scroll down to unit conversions, then we scroll to length, and then we press OK. Let's scroll down to meters. So we have 5 meters which we want to convert into centimeters. If I then press the catalog key, then scroll down to the unit conversions, then press OK. The first option is an arrow which will prompt us to convert a unit. We want to go from meters to centimeters, so if I press the catalog key and go back to the unit conversions, then length, we wish to convert to centimeters. If we execute, 5 meters is the same as 500 centimeters. We have to solve the simultaneous equation 2x plus 3y equals 6 and x plus y equals 3. If we go to the equation application, we have a simultaneous equation with two unknowns. We have 2x plus 3y equals 6. We have x plus y equals 3. If I press execute, you will find the solutions to be x equals 3, y equals 0. We have to solve the simultaneous equation x plus y subtract z equals 4, x subtract 2y plus 3z equals negative 6, 2x plus 3y plus z equals 7. If we go to the equation application, we have a simultaneous equation with 3 unknowns. We have the first equation, x plus y subtract z equals 4. We've got the second equation, x subtract 2y plus 3z equals negative 6. We've got the third equation, 2x plus 3y plus z equals 7. If I press the execute key, you will find the solutions to be x equals 1, y equals 2, z equals negative 1. We have to solve the equation 2x squared subtract x subtract 3 equals 0. If we go to the equation application, we have a polynomial of degree 2. We have 2x squared subtract x subtract 3 equals 0. And if I press execute, you will find the solution to be x equals 3 over 2, x equals negative 1. We have to solve the equation negative 3x cubed plus 7x squared plus 2x subtract 8 equals 0. If we go to the equation application, we have a polynomial of degree 3. We have negative 3x cubed plus 7x squared plus 2x subtract 8 equals 0, and if I press execute, you will find x to equal 2, x to equal 4 over 3, x to equal negative 1. We wish to solve the equation 4 times the natural log of x equals x, where x doesn't equal 0. If we go to the equation application, and then the third option for the solver, let's key in this equation. We have 4 multiplied by the natural log of x. Now here is the x key. Then we want to say equals x. You'll notice equals is a silver function. So we press shift, then the open bracket, and then we have 4 times the natural log of x equaling x. If I then press execute, we want to solve for x. We will use x equals 0 as an initial guess, and we will bound the solution in between negative 9 times 10 to the 9 and 9 times 10 to the 99. If we then execute this calculation, you will find x to equal 1.429, etc. We have to solve the equation 4 times the natural log of x equals x, where x doesn't equal 0. If we press the catalog key and the second option for function analysis, and then scroll down to the 6th option where we can solve equations using the solve function, and then press OK, we wish to solve 4 times by the natural log of x equals x. Now if we press the right arrow key, so now that the cursor is after the comma, what we input here is an initial value, such as 0. Now if I press the execute key, you will find x to equal 1.429, etc. We wish to solve the equation x squared plus 6 equals 15. We can solve this using the solve_n function on our calculator. If I press the catalog key and go to the second option for function analysis, we want to go to the fifth option where we can solve equations using solve_n. So let's press OK. Let's input the equation. We have x squared plus 6 equals 15. Then, after this, let's press the comma key and tell the calculator we are solving this equation for values of x, so we press the x key. If we press the comma key once again, we can now bound our solutions between two particular values, such as -10 and 10. Notice -10 is my lower limit, my upper limit is 10. So in other words, the calculator will solve the equation x squared plus 6 equals 15 for values of x, and it will find the x solutions in between -10 and 10. If we press execute, this pop-up appears which tells us more solutions may exist. If I press OK, the calculator has solved for us this equation for values of x. It found for us x to equal -3 and x to equal 3. Now, let us go back. What would happen if, say, I had my lower limit being 0 instead? When I come to execute, this pop-up appears which tells us more solutions may exist, and if I press OK, this time it only found the solution of x equals 3. So it made sense where the pop-up tells us that more solutions may exist. And this 3 makes sense because when we take a look at our values for which we've bounded x by, we've bounded x to be in between 0 and 10. And the -3 which we had before is not in between 0 and 10. 3 is in between 0 and 10. We have to solve the equation sine of 3x equals √3/2, where x is to be solved in between 0 and 2 pi radians. We can do this using the solve_n function on our calculator. If we go to the catalog and then the second option for function analysis, we want the fifth option which allows us to solve equations using solve_n. So we have the sine of 3x equaling √3/2. We need to tell our calculator to solve this equation for values of x, and then we will bound our values of x in between 0 and 2 pi. If we press execute, more solutions may exist which are outside of our domain. Let's press OK. We have x equals pi/9, x equals 2 pi/9, x equals 7 pi/9, x equals 8 pi/9, x equals 13 pi/9, and x equals 14 pi/9. The square root of -1 is known as I. It is a complex number. I is a Silver function. We can access this by pressing Shift, then 9. Here is I, and if I press execute, I is displayed. We also mentioned the square root of -1 is I. If I key in the square root of -1 and then press execute, we see this pop-up appear which tells us we have a non-real error, and that's because we are in the real mode. Let's change that by pressing Settings, the second option for complex mode, and then the second and the third option here allows us to display solutions in complex mode. Here is the rectangular form. Here is the r theta form. Let's display this in rectangular form. So now when we execute, you find the square root of -1 is equal to I. Before working out any calculation, let's go to the settings and let's turn on the complex mode such that we are in the form a plus bi. We are now in the form a plus bi. We are now required to work out the square root of -20. The square root of -20 is 2 root 5 I. As another example, we have to work out 3 subtract I over 2 plus I. Inputting this into our calculator, for the numerator we have 3 subtract I, and for the denominator 2 plus I. And working this out, we get 1 subtract I. We can use our calculator to work out the real and imaginary parts of a complex number. If we go to the catalogue and scroll down to the complex number option, and if we go to the fourth option for the real part, let's suppose we have the complex number 6 plus 9i. The real part of this complex number is 6. Now, if we go to the catalogue and scroll down to the complex number option and scroll down to the fifth option for the imaginary part, let's suppose now we want to work out the imaginary part of 6 plus 9i. You'll find that to be 9. So, we have used our calculator to work out the real and imaginary part of 6 plus 9i. We can use our calculator to find complex conjugates. If we press the catalogue key and then scroll down to the complex number option, and then the third option allows us to work out the complex conjugate. Let's suppose we want to work out the complex conjugate of 1/2 subtract 5/6 I. You will find the complex conjugate is 1/2 plus 5/6 I. We can use our calculator to find the modulus of a complex number. If we press the catalogue key and then scroll down to the complex number option and then number 1, let's suppose we want to work out the modulus of 3 plus 4i. Executing this calculation, we end up with 5. We can use our calculator to work out the argument of a complex number. if we press the catalog key and scroll down to the complex number option, and the second option allows us to work out the argument of a complex number. So let's suppose we want to work out the argument of the complex number 1 plus root 3 I. You will find the argument to be pi over 3. We can convert from rectangular form of a complex number to an exponential form of a complex number. Now let's suppose we have the complex number 1 subtract root 3 I. And let's suppose we want to convert this to exponential form. If we press the catalog key and go to the complex number option and then scroll down to here where we have the mod and the argument, and if we press execute and then execute once again, you will find we end up with 2 as our modulus and negative pi over 3 as our argument. In other words, the complex number is equal to 2e to the power of negative pi I over 3. We can use our calculator to convert from exponential form of a complex number to rectangular form of a complex number. Now, let's suppose we have the complex number 2e to the power of pi over 4 I. We wish to convert this to rectangular form. So if I press catalog and then scroll down to the complex number option and then scroll down, here is where we can convert to rectangular form. You will find 2e to the pi over 4i is equal to root 2 plus root 2i. Another way we can write this, we know the modulus is 2 and the argument is pi over 4. Here we have 2, and then if we press shift and then 8, this would indicate we now want to input the argument. And the argument is pi over 4. And what we wish to do is convert this to rectangular form. So, if we press catalog, scroll down to complex number, then scroll down, we want to convert to rectangular form, we get the same answer, root 2 plus root 2i. We can solve polynomial equations with complex roots, and we can do this using the equation application. Let's enter into the equation application. Before we do anything else, currently we are in the real mode. Let's change that by pressing the settings key and then the complex mode. We will change from real to the form a plus bi. We have to solve the equation x squared plus 2x plus 5 equals 0. What we have is a polynomial equation of degree 2. We have x squared plus 2x plus 5, and pressing the execute key, you will find x to equal negative 1 plus 2i, x to equal negative 1 subtract 2i. We have to solve the equation x cubed subtract 3x squared plus x plus 5 equals 0. We have a polynomial of degree 3. We have x cubed subtract 3x squared plus x plus 5 equals 0. And if we press the execute key, we see that x is equal to -1, x is equal to 2 plus I, x is also equal to 2 subtract I. We have to solve the equation x to the 4 plus x cubed subtract 11x squared subtract 31x subtract 20 equals 0. We have a polynomial of degree 4. We have x to the 4 plus x cubed subtract 11x squared subtract 31x subtract 20, and if I press the execute key, you find x to equal 4, x to equal -1, x to equal -2 plus I, and x to equal -2 subtract I. Let's enter into the graph and table application. When we enter into it, we see this screen here. The first thing we have is the type. Here we can select the type of graph we have. You can see currently we have selected a graph of the form y equals, and if you scroll through those, you can see the different types of graphs we can draw. Let's press back. We can also change the axis settings. Here is where we input in a function, and once we've inputted that function, we could either draw that graph or display a table of values. If we press the settings key, you can see different settings which we can adjust, and we can scroll through those accordingly. Currently, you will notice the type of graph we have selected is y equals. Here is where we have the variable key. We've got x's, which is what we use when we have a graph of the form y equals f of x. We've got theta, which is what we use when we've got polar graphs. We've got t, which is what we use when we've got parametric curves, and y, which is used when we've got graphs of the form x equals f of y. So let's see examples of those. Currently the type of graph selected is y equals, so I can have, for example, y equals x subtract 3. Let's press execute. If I now change the type to something involving r equals, that's polar form, I could have, for example, r equals cos theta. So pressing the variable key here, we've got theta. If I change the type to parametric, we could have, for example, x equals 3t squared subtract 4 and y equals 5t. If I then change the type to be of the form x equals f of y, I could have, for example, x equals 8y. So we can see by pressing this variable key will allow us to input in different functions depending on what type of graph we will be drawing. Let us input the function y equals x squared. If I press execute and then scroll down to draw a graph and then press OK, this pop-up appears. This pop-up allows us to change the settings of the axis. For now, let's select the first option, which allows us to draw this graph of y equals x squared. Here is the graph of y equals x squared. If we were to return back to the inputting section, we press the back key, and then we can further adjust our settings. Let's suppose we have the graph of y equals 1/2 x plus 2. Let's draw this graph. Here is the graph of y equals 1/2 x plus 2. Now you'd find that is shown in a solid line, which is blue. I can change that setting. If I press back and then highlight the graph y1 and then press the tools key, I can change the line style by going to the third option. We could have, for example, a dotted line. I could also change the line color to red, for example. And if I press back and then draw this graph, you can see now we've got a dotted red line instead of a solid blue line. You'd notice if I was to input a function such as y equals x squared, subtract 2x, subtract 3, and then if I go to the option where we can draw a graph, this pop-up appears. This pop-up is to adjust the axis settings. If we leave the settings as they are, we can draw the graph with those axis settings. We'd had a minimum x value of -6.3 and a maximum x value of 6.3. We had something similar in the y-axis. Now let's suppose we want to change those. Let's press the tools key and then the first option for view window. Here are the preset settings. So let's change the minimum x to be -5 and the maximum x to be 5. When we talk about x scale, currently it's set at 1, meaning we go up in steps of 1. So we have -5, -4, -3, etc. all the way up to 5. Let's change that to 2. We can do a similar thing with the y. Let's set the y minimum to be -10, the y maximum to be 5, and let's have a y scale of 2. We don't need to worry about t and theta minimum, or t and theta maximum, or t and theta pitch, because we are concerned with, for now, graphs of the form y equals f of x. If we press back, this screen appears. So now if we draw the graph with those new settings, you can see we've got our new scales for the x and y axis. If we wish to revert those settings, we can press the tools key, the first option for view window, then the first option for preset windows, and then we wish to initialize as such. So now, to convince you that we've done so, let's draw the graph with those preset settings. The graph is shown on the original axis. Let's suppose we have the graph of y equals x squared, subtract x, subtract 6. Let's draw this graph with the preset axis. Here is the graph of y equals x squared, subtract x, subtract 6. What we can do is use the zoom settings to zoom in and out. If we press the tools key and then go to the fifth option for zoom, we have various different zoom settings. It's often convenient to use Zoom Auto, which shows us the most important points of the graph, such as where it intercepts the x-axis, the y-axis and the minimum. If I go back to those zoom settings, it's also convenient to use the fifth option, which is zoom square. That creates a much narrower graph for us. We can also revert back to the original zoom settings, which is the eighth option for zoom original. We can also use the plus key to zoom in, as we see here, and we can also use the subtract key to zoom out, as we see here. We can pan using the arrow keys. So for example, to pan down, we can use the down arrow key. We can pan up using the up arrow key. We can pan left using the left arrow key. We can pan right using the right arrow key. We can enter in multiple functions into our calculator. Now here we've got y1. That means we can set into our calculator our first function, which is called y1. So for example, we could have our first function being x squared subtract 9. And if I press execute, you see that is already set. It's got a line type and a colour assigned to it. You see now what's highlighted is this y2. That prompts us to input in another function. We don't have to. We can straight away draw the graph y1 by going to draw graph, and you see here the graph of y equals x squared subtract 9. Let's press back. If we go back to the graph y2, we can enter in another function, such as y equals x subtract 5. That's got a different colour assigned to it, and that's to distinguish it from the line y1. We can later change those settings if we wish. So now, when we draw those graphs, we've got both graphs appearing. Let's zoom accordingly to see what's going on. We've got the graph of y equals x squared subtract 9, that's shown in blue, and the graph of y equals x subtract 5, that's shown in red. Let's suppose we have the graph of y equals 4x subtract 8, and also another graph such as y equals 2x plus 3. If we draw those graphs, you see the following appear. Let's use the fifth option to zoom accordingly, and let's zoom out to see both of those graphs. If we press the back key, what we can do is deselect one of those graphs. If we highlight a particular graph which we wish to deselect, such as this graph of y equals 2x plus 3, and if I press the tools key, you see currently that graph is selected. I can deselect it by pressing OK. And if I press back, and now drawing the graph, you will see this time only the graph of 4x subtract 8 has been shown. Now if I press back, you can actually see that this graph has been deselected. It's not filled in. I can select it back again by highlighting it, pressing the tools key, and then selecting this graph. And if I press back and then draw the graph, you can see that graph has now appeared again. We can explore variable coefficients with our calculator. let's suppose we've got the graph of y equals ax plus b, and let's key that in. We've got y equals ax plus b. Let's draw this graph. Currently, what you see is a horizontal line as such. In other words, a and b are 0, so we've got the line y equals 0. Now, let's modify this such that we can vary the values of a and b. If we press the Tools key and then go to the fourth option where we modify, you can now see a and b appear, and we've also got step. If I press the right arrow key, here you can see we've got y equals 1x plus 0. The yellow line is the previous graph which we had, which was 0x plus 0. I can continue to press right, which varies a. And notice we are going up in steps of 1. Similarly with b, we can increase b, and we can decrease b. Let's change the step to be 0.5, for example. So, with a, we could have y equals 0.5x plus 0, y equals 1x plus 0, y equals 1.5x plus 0, etc. Let's vary b as such. So here, shown in blue, is the graph of y equals 1.5x plus 2.5. And if I press execute on b, we can change b to be, for example, -4. And that sets the graph to be y equals 1.5x subtract 4. So we can vary a and b. We can draw graphs of the form y equals f of x. For this, we would have to use the x key here. For example, we can draw the graph y equals x subtract 1. And if we draw this graph, here is the graph of y equals x subtract 1. Let us draw the graph of y equals mx plus c. So, for example, we could have y equals 2x plus 1. If we draw this graph, here is the graph of y equals 2x plus 1. Let us draw the graph of y equals x squared. Inputting this in, we have y equals x squared, and if we draw this graph, here you can see y equals x squared. Let us draw the graph of y equals x cubed. Inputting this in, the graph of y equals x cubed, when we draw the graph, looks like this. Let us draw the graph of y equals x to the 4. If we input this in, the graph of y equals x to the 4 looks like this. Let us draw the graph of y equals 1 over x. Inputting this in, we've got the graph of y equals 1 over x looking something like this. Let us draw the graph of y equals 1 over x squared. Inputting this in, we've got the graph of y equals 1 over x squared looking something like this. Let us draw the graph of y equals 1 over x cubed. Inputting this in, we've got the graph of y equals 1 over x cubed, and if we draw the graph of y equals 1 over x cubed looks something like this. Let us draw the graph of y equals 1 over x to the 4. Inputting this in, we've got the graph of y equals 1 over x to the 4. And if we draw this graph, here is the graph of y equals 1 over x to the 4. We can draw graphs of rational functions. For example, let's draw the graph of y equals 2x plus 3 over 2x plus 5. Let's draw this graph. We get something looking like this. Now clearly we have horizontal and vertical asymptotes. So let's add those in. We have an asymptote at y equals 1, and we've also got a vertical asymptote at x equals negative 5 over 2. So we need to change the type to something involving x equals. We've got a vertical asymptote at x equals negative 5 over 2. Let's change the line to be dotted. Let's leave the colour as red. And here, let's change the line to be dotted and the line colour to be red. So now when we draw the graphs, we can see we have a vertical asymptote at x equals negative 5 over 2 and a horizontal asymptote at y equals 1. Let us draw the graph of y equals square root of x. Inputting this in, we have y equals the square root of x, and if we draw the graph, here is the graph of y equals square root x. Let us draw the graph of y equals sine x. Let's restrict the domain between negative 2 pi and 2 pi. If we draw this graph, the x minimum will set to be negative 3 pi and the x maximum will set to be 3 pi and the x scale will be pi. So if we draw this graph, here is the graph of y equals sine x between negative 2 pi and 2 pi. Let's draw the graph of y equals cos x, and let's restrict the domain between negative 2 pi and 2 pi. Let's change the x minimum to be negative 3 pi, the maximum x to be 3 pi, and the x scale to be pi. Let's now draw the graph. Here is the graph of y equals cos x in between negative 2 pi and 2 pi. Let's draw the graph of y equals tan x, and let us restrict the domain in between negative 2 pi and 2 pi. Let's draw this graph. Let's set the x minimum to be negative 3 pi, the maximum x to be 3 pi, the x scale to be pi, and if we draw the graph, here is the graph of y equals tan x. Now clearly we have asymptotes. Let's show those asymptotes. We have asymptotes at x equals minus 3 over 2 pi. We've also got asymptotes at negative pi over 2, pi over 2 and 3 pi over 2. So let's show those. Now first of all, you will notice that the type we have here is y equals. Let's change that. So this time we've got something of the form x equals. So we've got x equals negative 3 pi over 2. We've got x equals negative pi over 2. We've got x equals pi over 2 and x equals 3 pi over 2. Now currently these graphs are all in different colours. Let's show the asymptotes all in red and let's make them dotted. So if we press tools, this one's red, so that's fine. Let's change the line style to be dotted. Same with this one. Let's change the line style to be dotted, and let's change the colour to be red. And the same with this one. Let's change this to be dotted and the line colour to be red. And also the same with this one. Let's change the line to be dotted and the line colour to be red. So now let's draw this graph. Here you can see we've got the graph of y equals tan x with the asymptote showing at negative 3 over 2 pi, negative pi over 2, pi over 2 and 3 pi over 2. Let's draw the graph of arcsine x. The graph of arcsine x can be inputted into our calculator, and if we draw this, let's change the x minimum to be minus 2, the x maximum to be 2, the y minimum to be negative pi, the y maximum to be pi, and the y scale to be pi over 2. If we draw this graph, here is the graph of arcsine x. Let's draw the graph of arc cos x. Inputting this into our calculator, we've got y equals arc cos x. Let's draw the graph. Let's set the minimum x to be negative 2, the maximum x to be 2, the x scale will leave us 1. The minimum y, we will let that be negative pi over 2. The maximum y we will let be 3 pi over 2. Y scale we will let be pi over 2. And if we draw this graph, here we've got the graph of arc cos x. Let's draw the graph of arc tan x. Inputting this into our calculator, the graph of arc tan x, if we draw this, looks something like this. Now, we have two horizontal asymptotes, one at negative pi over 2 and one at pi over 2. So if I press the tools key, then view window, what we will do with the minimum y is we'll let that be negative pi. The maximum y we will let be pi. The y scale we will let that be pi over 2. Let us input the horizontal asymptotes. We've got y equals negative pi over 2 and y equals pi over 2. Let's change the color of these and the line style. So if I click tools, I'm happy with it being red, but the line style, let's change that to dots. And same thing with this. If I press tools, the line style, we will change to dots, and the color we will let be red. So now, if we draw this graph, you can see we've got the graph of y equals arc tan x with horizontal asymptotes at negative pi over 2 and pi over 2. Let us draw the graph of y equals cosec x. Now, the graph of y equals cosec x is the same as the graph of y equals 1 over sine x. Let us restrict the domain between negative 2 pi and 2 pi. If we draw the graph, let's set the minimum x to be negative 3 pi, the maximum x to be 3 pi, and the x scale to be pi. Now, let's draw the graph. Here is the graph of y equals cosec x. Now, let's show the asymptotes. We have vertical asymptotes, which are of the form x equals. So currently you can see the type is y equals. Let's change that so that the type is x equals. Now, we've got a vertical asymptote at x equals negative 2 pi. We've got another vertical asymptote at x equals negative pi. We've got another vertical asymptote at x equals 0. We've got another vertical asymptote at x equals pi. We've got another vertical asymptote at x equals 2 pi. Let's change the settings of each of these vertical asymptotes so that they are all red and all dotted. So we do that by pressing the tools key. Let's change this to be dotted. It's already red. For the next one, let's change the line style to be dotted, and let's change the color to red. For the next one, let's change the line style to be dotted and the line color to be red. For the next one, let's change the line color and the style to be dotted and red. And for the next one, doing the same thing, let's change this to be dotted and the line color to be red. So now let's draw the graph. You can see we've got the graph of y equals cosec x, and we've got vertical asymptotes at x equals negative 2 pi, negative pi, 0, pi, and 2 pi. Let's draw the graph of y equals sec x. Now sec x is the same as 1 over cos x, so we wish to draw the graph of y equals 1 over cos x. Let's restrict the domain between negative 2 pi and 2 pi. And if we draw the graph, let's set the minimum x to be negative 3 pi, the x maximum to be 3 pi, the x scale to be pi, and if we draw the graph, here we've got the graph of y equals sec x. Now, we've got vertical asymptotes which we can also show. Let's add those on. Those are of the form x equals. So we need to change the type from y equals to the form where we have x equals. So we have a vertical asymptote at x equals negative 3 pi over 2. We've got another vertical asymptote at x equals negative pi over 2. We've got another vertical asymptote at x equals pi over 2. And we've got another vertical asymptote at x equals 3 pi over 2. Let's change the line color and the line style to all be red and dotted for these vertical asymptotes. We can do that by pressing the Tools key. The line style I want to be dotted, the line color is already red. For the next one, I want the line style to be dotted and the color to be red. For the next one, I want the line style to be dotted and the color to be red. And for the next one, the line style I want to be dotted and the color to be red. So let's draw that graph. You can see we've got the graph of y equals sec x between negative 2 pi and 2 pi, and we've got vertical asymptotes at x equals negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Let's draw the graph of y equals cot x. Y equals cot x is the same as y equals 1 over tan x. Let's restrict the domain between negative 2 pi and 2 pi. Now, when we come to draw the graph, let's set the x minimum to be negative 3 pi, the x maximum to be 3 pi, and the x scale to be pi. When we draw the graph, here we've got the graph of y equals cot x. Now, we have vertical asymptotes, which we can also show. Those are of the form x equal. Now, you can see the type so far is y equals. Let's change that so we have x equal. So, we've got a vertical asymptote at x equals negative 2 pi. We've got a vertical asymptote at x equals negative pi. We've got another one at x equals 0, another one at x equals pi, another one at x equals 2 pi. Let's change the line style and colour for all these vertical asymptotes by pressing the tools key. Let's make them all dotted and red. So for this one, let's change the line style to be dotted and the line colour to be red. For this one, let's change the line to be dotted and the line colour to be red. For this one, let's change the line to be dotted and the line colour to be red. And for this one, let's change the line to be dotted and the colour to be red. So now let's draw the graph. Here we've got y equals cot x with vertical asymptotes at x equals negative 2 pi, x equals negative pi, x equals 0, x equals pi, and x equals 2 pi. Let us draw the graph of y equals e to the x. We have y equals e to the x, and if we draw this graph, here is the graph of y equals e to the x. Let us draw the graph of y equals the natural log of x. We have y equals the natural log of x, and if we draw this graph, here is the graph of y equals the natural log of x. Let's draw the graph of y equals 2 to the power of x. If we draw this graph, here is the graph of y equals 2 to the power of x. Now, the inverse function of this will be y equals log base 2 of x. And if we draw this graph, here we've got the graph of y equals log base 2 of x. So the graph of y equals 2 to the power of x and the graph of y equals log base 2 of x are reflections of each other in the line y equals x. Let's verify that. So, if I press the tools key, then go to the sketch option. The fourth option allows us to show the inverse. Now currently you can see here we've got y equals 2 to the x flashed in yellow. So this means we can select this to show its inverse. And if I do that, you can see in green we've got the graph of y equals log base 2 of x. It is the inverse of y equals 2 to the x. Let us draw the graph of y equals the mod of ax plus b. Now, if I press the catalog key and then the fourth option for numeric calculation and then the third option for absolute value, that allows us to draw graphs involving mod. So we could have, for example, y equals the mod of 2x plus 1. And if we draw this graph, here you can see we've got the graph of y equals the mod of 2x plus 1. Let's draw the graph of y equals hyperbolic sine x. If we go to the catalogue and then scroll down to the option for hyperbolic calculation and select the first option for hyperbolic sine, we wish to draw the graph of y equals hyperbolic sine x. And if we draw this graph, here is the graph of y equals hyperbolic sine x. Let's draw the graph of y equals hyperbolic cosine x. If we press the catalog key and then go to the hyperbolic calculation option, the second option allows us to input hyperbolic cosine. So we wish to draw the graph of y equals hyperbolic cosine x. And if we draw this graph, here is the graph of y equals hyperbolic cosine x. Let's draw the graph of y equals hyperbolic tan x. So, if we press the catalog key and then go to the hyperbolic calculation option, the third option allows us to input hyperbolic tan. So we wish to draw the graph of y equals hyperbolic tan x. And if we draw this graph, here is the graph of y equals hyperbolic tan x. Now, we've got horizontal asymptotes at y equals -1 and y equals 1. So let's show those. So we've got a horizontal asymptote at y equals -1 and another horizontal asymptote at y equals 1. Let's change the line style to involve dots for our asymptotes, and let's make them red. So now if we draw the graph, you can see we've got the graph of y equals hyperbolic tan x with horizontal asymptotes at y equals -1 and y equals 1. Let us draw the graph of y equals inverse hyperbolic sine x. If we press the catalog key and then go to the hyperbolic calculation, the fourth option allows us to input the inverse hyperbolic sine. So we want to draw the graph of y equals the inverse hyperbolic sine of x. And if we draw this graph, here you can see we've got the graph of y equals inverse hyperbolic sine x. Let us draw the graph of y equals inverse hyperbolic cosine x. If we press the catalog key and then scroll down to hyperbolic calculation, the fifth option allows us to input the inverse hyperbolic cosine. So we wish to draw the graph of y equals inverse hyperbolic cosine of x, and if we draw this graph, here we've got the graph of y equals inverse hyperbolic cosine x. Let us draw the graph of y equals inverse hyperbolic tan x. If we go to the catalogue and then scroll down to the hyperbolic calculation, the sixth option allows us to input the inverse hyperbolic tan of x. So we want to draw the graph of y equals inverse hyperbolic tan of x. And if we draw this graph, we've got something looking like this. Now, we have vertical asymptotes at x equals -1 and x equals 1. So let's show those. If I press the Tools key and then View Window, let's set the minimum x to be -2, the maximum x to be 2. Now, currently the type is y equals, we want that to be x equals, so let's change that. So we have a vertical asymptote at x equals -1. We've got another vertical asymptote at x equals 1. Let's change the line style and colours to be dots and red. Let's draw the graph. Here you can see we've got the graph of y equals inverse hyperbolic tan x with vertical asymptotes at x equals -1 and x equals 1. We can draw graphs of the form x equals f of y. Now, if we change the type of graph to the fourth option where we have x equals, this allows us to input functions of the form x equals f of y. So we could have, for example, x equals 8y. And if we draw this graph, here is the graph of x equals 8y. To draw polar equations, we first of all need to change the type of graph we have. Currently it's set at y equals. If I press OK and then the first option for type, we want to go to the second option which allows us to enter in polar equations. For example, we could enter in the polar equation r equals cos theta. Remember, when we press this key, we load up theta. So if I draw this graph, here is the graph of r equals cos theta. Let us draw the graph of r equals a over cos theta. Let's input this into our calculator. We have r equals a over cos theta. Let's draw this graph. And if I press the Tools key and the fourth option for modify, let's vary a and explore what happens. If a is equal to 1, we have a vertical line at x equals 1. When a equals 2, we have a vertical line at x equals 2. This also applies for the negative a's. For example, when a is equal to -3, we have a vertical line at x equals -3. In general, r equals a over cos theta gives us a vertical line at x equals a. Let's draw the graph of r equals a over sine theta. Let's input this into our calculator. We have r equals a over sine theta. Let's draw this graph. If I press the Tools key and the fourth option for modify, let's vary a. When a equals 1, you see we have a horizontal line at y equals 1. when a equals 2, we have a horizontal line at y equals 2. And this also applies for negative values of a. For example, when a equals negative 2, we have a horizontal line at y equals negative 2. In general, r equals a over sine theta gives us a horizontal line at y equals a. Let's draw the graph of r equals a theta. Inputting this into our calculator, we have r equals a theta. Let's draw the graph. Before that, let's change the axis settings. Let's change the x minimum to be negative 25, the x maximum to be 25, the x scale to be 5, the y minimum to be negative 25, the y maximum to be 25, the y scale to be 5. Let's draw this graph. Let's press the Tools key and the fourth option for Modify, and let's vary a. You can see as we vary a, we end up with the spiral. Let's draw the graph of r equals a. Let's input this into our calculator. We have r equals a. Let's draw this graph. Let's change the x minimum to be negative 8, x maximum to be 8. We'll leave the x scale as 1. Let's change the y minimum to be negative 8, the y maximum to be 8, and the y scale let's leave as 1. Let's draw the graph. Let's press Tools, the fourth option for Modify, and let's vary a. Now, when a equals 1, you can see we've got a circle with centre at the origin and radius 1. When r equals 2, same thing. We've got the centre at the origin, but this time the radius is 2. And we can explore with that even further by varying a. In general, r equals a gives us a circle with radius a and centre at the origin. Let's draw the graph of r equals a cos theta plus b sin theta. Let's input this into our calculator. We have r equals a cos theta plus b sin theta. Let's draw this graph. Let's change the x minimum to be negative 8, the x maximum to be 8, the x scale will leave us 1. The y minimum, let's set that to be negative 8, the y maximum, let's set that equal to 8, the y scale will leave us 1. Let's draw this. If I press Tools and the fourth option for Modify, we can vary a and b. Now, varying a, let's see what happens. You can see here we've got a circle with the y coordinate of the centre lying along the x-axis. Let's make a 0. Let's make b 1. You can see here we've got a circle with the x-coordinate of the centre lying along the y-axis. Now, let's change a to be 4. We have a circle with centre 2 across, 0 up. And the radius here is 2. Let's change b to be 3. We have a circle with centre 2, 1.5 and radius 5. In general, r equals a cos theta plus b sin theta gives us a circle with centre a over 2, b over 2, and radius the square root of a squared plus b squared. Let's draw the curve r equals a cos n theta. Inputting this into our calculator, we have r equals a cos n theta. Let's draw this graph. Now, if I press the tools key and the fourth option for modify, let's vary a. So far, when we vary a with n equaling 0, we have a circle. Now, let's let n equal 1. Here we've got a circle. When n is 2, we end up with a rose petal. When n is 3, we still have a rose petal, and we can explore that by varying n. Now, you will notice when n is an odd number, we have n petals. However, when n is an even number, we have 2n petals. And you will also notice the radius is equal to a. In general, r equals a cos n theta gives us a rose petal curve where n is greater than or equal to 2. When n is even, we have 2n petals. When n is odd, we have n petals. Let's draw the curve r equals a sine n theta. Let's input this into our calculator. We have r equals a sine n theta. Let's draw this graph. If I press the tools key and the fourth option for modify, we can vary a and n. You can see when I increase a, so far nothing is happening, and that's because we've got the sign of 0. Let's change n to equal 1. Now let's vary a. Here you can see we've got a circle. Let's increase n to be 2. What you can see now is we have a rose petal. And as we vary n, you can see the effect of varying n. Now, you will notice when n is odd, we have n petals. However, when n is even, we have 2n petals. In general, r equals a sine n theta gives us a rose petal curve with radius a where n is greater than or equal to 2. When n is odd, we have n petals. When n is even, we have 2n petals. Let us draw the graph of r equals a plus minus b cos theta, where a and b are both greater than 0. This type of graph is called a limacon. Let's input this into our calculator. We have r equals a plus b cos theta. Let's draw this graph. Let's press the tools key, the fourth option for modify. Let's vary a and b. Now so far we know that a and b both have to be greater than 0. So let's change those accordingly. Now, in the case where b is greater than a, such as what we see here, you can see we've got a limacon with a loop. What would happen if a is equal to b? For example, a equals 2, b equals 2. Well, here we've got a cardioid, and notice the distance from the y-axis to this point here is twice a, and the distance from the x-axis to here is a. What would happen if we had a being greater than b? For example, a being 3 and b being 2. Well, in this case, you can see we've got a dimple. What would happen if a is greater than or equal to 2b? For example, a is 2 and b is 1. Here we have something which is convex, and notice this bit is flat. Let's draw the graph of r equals a plus minus b sine theta, where a and b are both greater than 0. This type of graph is called a limacon. Let's input this into our calculator. We have a plus b sine theta. Let's draw this graph. Let's press the tools key and the fourth option for modify. We know so far a and b have to be greater than 0, so let's change a to be 1 and b to be 1. Now, in the case where b is greater than a, so for example, b equaling 2 and a equaling 1, you can see we've got a loop. In the case where a and b are both equal to each other, for example, a equaling 2 and b equaling 2, we have a cardioid. In the case where a is greater than b, so for example, a is 3 and b is 2, you can see here we've got a dimple. In the case where a is greater than or equal to 2b, for example, a is 2 and b is 1, we have something which is convex, and notice here this portion is flat. Let us draw the graph of r equals the square root of a squared cos 2 theta. This is known as a lemniscate curve. Let's input this into our calculator. We have r equals the square root of a squared multiplied by cos 2 theta. Let's draw this graph. If I press the tools key and the fourth option for modify, let's vary a. You can see we have a loop as such, and the radius of this is a. Let's draw the graph of r equals the square root of a squared sine 2 theta. This type of curve is known as lemniscate. Let's input this into our calculator. We have r equals the square root of a squared multiplied by sine 2 theta. Let's draw the graph. Let's press the tools key, the fourth option for modify, and let's vary a, as we see here. What you see is we have a radius of a. In general, r equals the square root of a squared sine 2 theta has a loop with its radius being a. We can use our graph to plot parametric equations. Currently, you see the type of graph we have is y equals. If I select this, and then the first option for type, the third option allows us to enter in parametric equations. And you see those appear as a pair. We've got xt1, yt1, which is a single graph. Now, we could have, for example, x equals 4t squared. Now, here is the t key. So we've got x equals 4t squared, our next equation could be, for example, y equals 8t. Now, if we draw these graphs, you can see we've got the graph of x equals 4t squared and y equals 8t shown here. We can restrict the domain using our calculator. Now, let's suppose we have the graph of y equals x squared subtract 1. If we draw this graph as it is, here is the graph of y equals x squared plus 1. Now, so far, the domain of this graph is not restricted, but we can restrict it. If we were to restrict the domain, notice the cursor is to the right of the function as it is. If I press the comma key, then we need to open up square brackets. To do this, press Shift, then 4, and let's suppose the lower limit of my domain is -3, and to define an upper limit of the domain, I press the comma key again. I can now input in my upper limit, for example 5. We need to close off with the square brackets, so we press Shift and this time the 5 key. And if we draw this graph, let's zoom out so we can see what's going on. Here we've drawn the graph of y equals x squared subtract 1, and indeed we have restricted the domain from -3 to 5. What we'll do is we'll modify the x values to see that more clearly. So we could have the minimum x being -7 and the maximum x value being 7. So now if we draw this graph, let's scroll down, you can see more clearly how we've restricted the domain. We can use our calculator to draw piecewise functions. Now let's suppose our first function is y equals 6 subtract 2x. What we'll do is we'll set a domain for this. So let's press the comma key and then open up a square bracket. And let's set a lower limit of -infinity. Now there's no infinity button, but we can use a really negative number, such as -9 times 10 to the 99. Now for the upper limit, let's use something like 1, and let's close the square brackets. For the second part of the piecewise function, we could have y equals x squared plus 4, where for our domain, we have x being greater than or equal to 1, so our lower limit would be 1, and our upper limit will be infinity, but there's no infinity number, so let's use something really large, something like 9 times 10 to the 99. And let's close the bracket. So now, if we draw this, and then if we go to the zoom auto feature, and what we'll do is we'll pan accordingly so we can see what's going on around this point. You can see we've sketched a piecewise function. Let's suppose we have the graph of y equals sine x. You will notice so far we are in radians. So when I come to draw this graph, let's use the x scale to be pi to clearly see what's going on. You can see here we've got the graph of y equals sine x, but in radians. Let's suppose we want to show that in degrees instead. Well, if I press the settings key, the first option for angle, we can change the angle unit to degrees. So now if I draw the graph, here we are in degrees. But of course, we need to adjust the x-axis. So let's do that. If I press Tools, then the first option for View Window, let's change the minimum x to be minus 400, the maximum x to be 400, the x scale, let's change that to 180. If we draw the graph, you can now see we are in degrees instead of radians. Let's draw the graph of y equals x squared plus 2x subtract 3. Let's now use the auto zoom feature as shown. If I press the Tools key and then go to the third option, which is Trace, and if I use the cursor keys, what you can see is the cursor moves along the graph. And what that does for us is it tells us what a particular y value be for a particular x value. So you can see, for example, here, when x is 3, y is 12. And we can continue scrolling. For example, when x is 4, y is 21. Now what would happen when y is 5? Well, if I type in 5 and then execute, you will find y to be 32. Let us draw the graph of y equals x squared plus 2x subtract 3. If we draw this graph, the following appears. Let's use the auto zoom feature. If I press the Tools key and then the second option for graph solve, what we can do with the first option is find the roots of the graph. We've got a root over here at x equals -3, and if I press the right arrow key, we've got another root at x equals 1. Let us draw the graph of y equals x squared plus 2x subtract 3. If we draw this graph, the following appears. Let's use the auto zoom feature. We can find the y-intercept of a graph. If I press the Tools key and then the second option for graph solve, and if we scroll down to y-intercept, you can see the y-intercept when x is 0, y is -3. Let us draw the graph of y equals x squared plus 2x subtract 3. If we draw this graph, the following appears. Let's use the auto zoom feature. What we can also do is find a particular y value given a particular x value. If I press the Tools key and then go to graph solve and then scroll down to the yCalc, when x is -2, this will calculate for me the corresponding y. The corresponding y value will be -3. Let us draw the graph of y equals x squared plus 2x subtract 3. If we draw this graph, the following appears. Let's use the auto zoom feature. We can find a particular x value given a particular y value. If I press the tools key and then go to the second option for graph solve and then scroll down to xCalc, if we know a particular y value, we can find the x from there. So for example, if we have y equals 5, we can see we've got a solution here at -4 and another solution at 2. Let's suppose we have the graph of y equals 2x subtract 3. Let's draw this graph. Drawing the graph and zooming out, we have something looking like this. If we wish to sketch the inverse of this graph, if we press the tools key, then scroll down to sketch, the fourth option would draw for us the inverse. Here is the inverse to the equation y equals 2x subtract 3. Let us input the function y equals x squared plus 2x subtract 3. Let us input in another function y equals x plus 3. Let's draw those graphs. As we see here, if I press the tools key and then go to the fifth option, let's use the zoom auto feature. And let's adjust accordingly so we can clearly see what's going on. If I press the tools key and then go to the second option for graph solve, what we can do is find the intersection point. That's the fourth option. We've got an intersection point here when x is equal to -3, y is equal to 0, and pressing the right arrow key, we see the other intersection point when x is equal to y is equal to 5. Let's suppose we've got the graph of y equals cos x. Let's draw this graph. Let us change the x scale to be pi. Let's change the minimum y to be -5 and the maximum y to be 5. Let's leave the y scale as 1. Let us draw this graph. Here is the graph of y equals cos x. What we can do is apply transformations to this graph. So let's press back. With this function y1, we can apply transformations to it to get a new function y2. But first, we have to let y2 equal something involving y1. So if I press the variable key and the second option for function, we can load up the function y1, which is equal to cos x. And now we can apply transformations to the function y1, which is equal to cos x. So let's go back. What we could also do is say have a over here. So we've got a multiplied by the function y1. So now if we draw this graph and then modify, currently A is at -2, but we can change that. A can be -1, A can be 0, in which case we'd have a horizontal line at y equals 0. And you can see the effect of increasing A. So let's go back. Let us create a third function where this time we are transforming in the x direction. Now again, let's load up the graph y1. So we click the variable key, the second option for function, and then we will select the graph y1, which is cos x. Now let's suppose we want to transform in the x direction. Well, in this case, we'd have to open up a bracket and then key in x, and then say we could, for example, add on b. Let's close bracket. Now before we draw this graph, let's deselect graph y2. Drawing the graph, we press the tools key and the fourth option for modify. We can increase or decrease b. Now let's change the step for b to be pi over 2. So now we see clearly the effect of changing b in the x direction. In this case, we'd have a translation by vector -b, 0. Let's go back. What we could do instead is, say for example, multiply the x by b. What would the effect be in this case? Let's draw this graph. Let's click the tools key, the fourth option for modify. Let's change the step to be 1. If we change b to equal 1, for example, you can see clearly what's happening when we increase or decrease b. We are multiplying x by b, which means in terms of our transformation, we have a stretch scale factor 1 over b in the x direction. So, we've explored how to visualize transformations on our calculator. We have to complete the table of values for y equals 4x subtract 4. We see in the table the values of x go from -2 to 3. Let us input in this function. We have y equals 4x subtract 4. If we go to the option where we can display the table, you see here we have values of x going from 1, 2, 3, 4, 5. Let's change that. If we press the tools key and then set the table domain, the first option for range, we want to start at -2. We want to end at 3. The step is 1 because we are going up in ones in the x. When we now display the table, you see when x is equal to -2, y is equal to -12. When x is equal to -1, y is equal to -8. When x is equal to 0, y is equal to -4. When x is equal to 1, y is equal to 0. When x is equal to 2, y is equal to 4, when x is equal to 3, y is equal to 8. If I press the back key, we can also draw this graph, and if we adjust with the zoom settings, we have the graph of y equals 4x minus 4. We can use our calculator to draw cobweb and staircase diagrams. These can be used to show how convergence takes place. To begin with, we have to go to the recursion application. Once we enter into it, we see this screen here. We have to use the iteration xn plus 1 equals 3 subtract xn cubed all over 4 with x1 equaling 0.5 to find x4. We then have to draw a cobweb diagram to show how convergence takes place. First of all, you will notice instead of us having x's, here we've got u's. That doesn't make any difference for us. Let's key in the iterative formula. We have 3 subtract. Now, to get the un function, we press catalog, then we go to recursion, and then we go to the second option for un. So we have 3 subtract un cubed all over 4. We've got the iterative formula, un plus 1 equals 3 subtract un cubed all over 4. Now, here we've got u0. We want to change that to u1. If I go to viewing setup, the first term is u1. Now, our first term is 0.5. Before we do anything else, if we go back to viewing setup and then the fourth option for set table domain, we want to start at 1, which means u1, and we want to end at 4, which means u4. The other thing we want to do from viewing setup, if we go to the fifth option, un start should be 0.5, which is the same as our initial value for u, which in this case, u1 equals 0.5. So, having inputted all this information in, let's execute. You can see we have u1, which is 0.5, u2, which is 0.71875, u3, which is 0.657173157, and u4, which is 0.6790455,798. Now, if I press the Tools key, then the fourth option for Web Graph, and draw the graph, we've got the line y equals x, and also the graph of 3 subtract x cubed all over 4. Let's zoom in around this region. So we press Tools, the fourth option for zoom. We will create a box. So let's create a box to clearly see what's going on. And we will create our box around this region here, as we see. So if I press OK, we have a starting value of 0.5. Then we have u2. Then we have u3. Then we have u4. Here is the cobweb diagram. We have to use the iteration xn plus 1 equals the natural log of xn plus 3 over the natural log of 3 with x1 equaling 0.5 to find x4. We then have to draw a staircase diagram to show how convergence takes place. As before, here we've got u's instead of x's. That doesn't make any difference to us. Let's key in the iterative formula. We have the natural log of un plus 3 over the natural log of 3. We don't have u0, instead we've got u1, so let's go to viewing setup. The first term is u1, which is equal to 0.5. If we go to viewing setup, the fourth option for set table domain, we start at u1, we finish at u4, and if we go back to the viewing setup, and then the fifth option for set web graph start, un will start at 0.5, which matches with our initial value of u. Let's now execute. We have u1, which is 0.5, u2, which is 1.140313996, u3, which is 1.29324269, u4, which is 1.326256942. If we now press the tools key and the fourth option for web graph and draw the graph, we've got the line y equals x and the graph of the natural log of x plus 3 over the natural log of 3. Let us create a box to zoom around. Such as this one. We start off with u1 equaling 0.5. Then we have u2, which is 1.14, etc. Then we have u3, which is 1.29, etc. Then we have u4, which is 1.32, etc. Here is the completed staircase diagram. We can use our calculator to draw equations of circles. If we go to the conic graphs application, then the first option for Cartesian, you will see this screen here. We have to draw the graph of x plus 1 all squared plus y subtract 1 all squared equals 2 squared. If we scroll down to the highlighted option here and then press OK, we can enter in the values of h, k and r. If we have x plus 1 all squared, that means h is equal to -1, because we have x subtract -1 all squared, which is the same as x plus 1 all squared. K here would be 1 and r would be 2. If we draw this graph, you can see we have the graph of x plus 1 all squared plus y subtract 1 all squared equals 2 squared. We have a circle with centre -1, 1 and radius 2. We have to draw the graph of x squared plus y squared subtract 4x subtract 6y subtract 3 equals 0. If we scroll down to the highlighted option here, in this case, a is equal to 1. That allows us to have x squared plus y squared, ensuring we have a circle. B is -4. C is -6. And D is -3. If we draw the graph, let's zoom accordingly. Here is the graph of x squared plus y squared, subtract 4x, subtract 6y, subtract 3 equals 0. We have the centre being at 2, 3, and the radius being 4. To draw ellipse graphs, we have to go to the conic graphs application. Once we enter into it, we see this screen here. In this example, we have to draw the graph of, first of all, the Cartesian equation x squared over 5 squared plus y squared over 3 squared equals 1, and then the equivalent parametric equation x equals 5 cos t and y equals 3 sin t. Let us draw the Cartesian equation. If we scroll down to the option highlighted here, we have h and k equaling 0. A is 5 and b is 3. Let's execute. Let's zoom out. Here we have the ellipse. If I press the tools key, then the second option for graph solve. Here is where the focus is. Here is where the other focus is. If I press the tools key, the second option for graph solve, and then the fourth option for E, that's calculated as 0.8. So we have drawn for us the ellipse x squared over 5 squared plus y squared over 3 squared equals 1. And we've shown the foci as well. Let us return to this screen here. Let's go to the parametric option. Then if we scroll down to this option, we have the same value of A and B. Again, H is 0, K is 0. If we draw this graph as before, here is our ellipse. If I press the tools key, the second option for graph solve, again, we've got the focus at 4 and minus 4. And if I go to the graph solve option, I can also find E, which is 0.8. To draw hyperbolic graphs, we begin by going to the conic graphs application. Once we enter into it, we see this screen here. In this example, we have to draw the graph of, for the first part, the Cartesian equation x squared over 5 squared, subtract y squared over 3 squared equals 1, and then for the second part, the equivalent parametric equation x equals 5 sec t and y equals 3 tan t. If we go to the Cartesian option, and then scroll down to this highlighted option, we have h and k equaling 0, and here a is equal to 5 and b is equal to 3. Let's now draw this graph. Let's zoom out accordingly. If I press the tools key and the second option for graph solve, we've got the focus here and here. If I press the tools key, the second option for graph solve, we can also find E, which is shown here to be 1.16, etc. If I press the tools key, the second option for graph solve, and then the fourth option for asymptotes, we can show the asymptotes. Those have gradient 0.6. Let's press back. If I go to the parametric option, and then if we scroll down to the highlighted option here, H and K are both equal to 0. We have A, which is 5, and B, which is 3. If we draw this graph, we have the same graph as we did before. If I press Tools, then the second option for graph solve, we've got the focus here and here. If I press Tools, then the second option for graph solve, we can see what E is. If I press Tools, then the second option for graph solve, we can also show the asymptotes. As before, we have a slope of 0.6. We are given y equals x squared plus 8. We have to find the value of dy over dx when x equals 5. If we press the catalog key and the second option for function analysis, we will be using the first option for the first derivative. We want to differentiate x squared plus 8 and then work out the value of dy over dx at the point x equals 5. And if I execute, you will find that to be 10. We are given y equals x squared subtract 3x. We have to find the value of the second derivative d squared y over dx squared when x equals -2. If we press the catalog key, then go to the second option for function analysis, we will be using the second option where we can use the second derivative. We want to work out the second derivative of x squared subtract 3x and work out the value of the second derivative at x equals -2. And working this out, you will find that to be 2. We are given y equals x cubed subtract 3x squared plus 2x. We have to find the equations of the tangent and the normal to the curve at x equals 2. Let's go to the graph and table application. Let's key in the equation x cubed subtract 3x squared plus 2x. Let's draw this graph. Let's set the x minimum to be -2, the x maximum to be 4, the x scale will leave us 1, the y minimum, let's set that to be -5, the y maximum, let's set that to be 5, the y scale will leave us 1. Let's draw the curve. We see something like this. Now, if I press the settings key and go to the fifth option where we have derivative, let's turn this on. If we also go down to where it says show equation, we need to make sure this is also on. Now, if I press the tools key and then go to the sixth option for sketch, we can sketch a tangent line. We can select x to equal 2, and if I press execute, we see the tangent to the curve at the point x equals 2 as equation y equals 2x subtract 4. Let's press the back key. If I now press the tools key, go down to sketch, then the third option for normal line, we want the normal at the point x equals 2. And if I press execute, you can see the normal has equation y equals negative 1/2 x subtract 1 at the point x equals 2. So, you can see the curve, the equation of the tangent, and the equation of the normal at the point x equals 2. We have to find the x-coordinates of the stationary points of the curve y equals a quarter x to the 4, subtract 2x cubed plus 4x squared. We can do this using the solve n feature. If I press the catalog key, the second option for function analysis, then the fifth option for solve n, what we need to do is differentiate y with respect to x. So, we press the catalog, then go to function analysis, then the first option for d over dx. We have the function y equals 1/4 x to the 4 subtract 2x cubed plus 4x squared. We wish to differentiate this at the point x equals x. We will then set the result equal to 0 and then solve for x. And in doing so, you will find x to equal 0, x to equal 2, and x to equal 4. And these are the x-coordinates of the stationary points of the given curve. We are given that y equals x cubed subtract 3x squared subtract 9x. We have to determine the nature of the stationary points. For us to do this, we have to differentiate y, then we have to set that result equal to 0, and solve for x to find the stationary points. We can do this using our calculator. If we press the catalog key, then go to the second option for function analysis, then the fifth option for solve n, then if I go back to the catalog, the second option for function analysis, and the first option for first derivative, we want to differentiate x cubed subtract 3x squared subtract 9x at x equals x, then set the result equal to 0. And if we do that, we have negative 1 and 3. So the stationary points are at x equals negative 1 and x equals 3. We can now determine the nature of the stationary points. If I press the catalog key, then the second option for function analysis, then the second option for the second derivative, we have the function x cubed subtract 3x squared subtract 9x at x equals negative 1. The second derivative is equal to negative 12, meaning we have a maximum. If we repeat this step, we have the function x cubed subtract 3x squared subtract 9x at x equals 3 the second derivative is equal to 12, which means when x is equal to 3, we have a minimum. So, at x equals -1, we have a maximum. At x equals 3, we have a minimum. We are given that y equals x cubed, subtract 9x squared plus 15x plus 4. We have to graph the curve and show the maximum and minimum points. We can do this using the graph and table application. Let's enter into it. Let's key in the equation x cubed subtract 9x squared plus 15x plus 4. Let's draw the graph. Let's set the x minimum to be -5, the x maximum to be 10, the x scale will leave us 1. The y minimum, let's set that to be -30, the y maximum, let's set that to be 30, and the y scale, let's set that to be 5. Let's draw this graph. We see this. If I press the Tools key, then go to the second option for Graph Solve, then the second option for Maximum Value, that's shown here, and if I press OK, we've got the maximum at 111. If I press the Tools key, the second option for Graph Solve, then the third option for Minimum Value, the minimum value is here at 5, -21. So we have the maximum at 111, the minimum at 5, -21. We have to work out the integral of x to the -3/2 plus 6x squared between the limits of x equals 1 and x equals 4, all with respect to x. We can key this into our calculator. If we press the catalog key, then the second option for function analysis, then the third option for integration, we have x to the power of -3/2 plus 6x to the power of 1/2. We have a lower limit of x equals 1, an upper limit of x equals 4, and if we press execute, you will find the result to equal 29. We have to find the area bounded by the curve y equals x to the half plus 12x to the -1/2, where x is a real number and greater than 0, the x-axis, and the straight lines with equations x equals 1 and x equals 4. Let's go to the graph and table application. Let's key in the curve x to the 1/2 plus 12x to the -1/2. Let's draw this graph. Let us set the x minimum to be -5, the x maximum to be 10, the x scale will leave us 1, the y minimum, let's set that to be -10, the y maximum, let's set that to be 20, and the y scale, let's set that to be 5. Here is the graph of y equals x to the 1/2 plus 12x to the 1/2. If we press the tools key, then the second option for graph solve, then the fifth option for the integration, we will use the first option where we can select a lower limit and an upper limit. The lower limit is x equals 1. The upper limit is x equals 4. And working this out, you will find the area to equal 28.67. We have to find the area bounded by the straight line y equals x plus 4 and y equals negative x squared plus 8x subtract 6. If we go to the graph and table application, let us enter in the first equation, y equals x plus 4. We've got the second equation, y equals negative x squared plus 8x subtract 6. Let us change the line colour to blue. Let's draw the graph. We will set the x minimum to be negative 5, the x maximum to be 10, the x scale will leave us 1. The y minimum we will set to be negative 5, the y maximum we will set to be 15, the y scale we will set to be 5. Let's draw the graph. Here we've got both graphs. If I now press the tools key, the second option for graph solve, then the fifth option, we want the area between two curves. So we go to the third option for intersection. We've got an intersection point here at x equals 2. Another intersection point at x equals 5. The area is equal to 4.5 units squared. We can solve inequalities using our calculator, and we can do this using the number inequality application, which we can access by pressing B. Once we enter into the application, we see this screen here. We have to solve the inequality x squared subtract x subtract 6 is greater than 0. Here we have a quadratic inequality of degree 2. Highlighted is something which matches up to the given quadratic inequality. So let's press OK. We then match the inequality type with what we have in the question. We have something which is greater than 0 as highlighted. Let's press OK. We have x squared subtract x subtract 6 is greater than 0. And if I press execute, you will find x to be less than negative 2 or x to be greater than 3. We can represent inequalities using our calculator, and to do this, we'd have to go to the graph and table application. We have to represent the following inequalities on a graph. We have y being greater than or equal to x squared plus 2x subtract 3. We have y being less than x plus 3. We have x being less than 1. We have x being greater than or equal to negative 2. We also have to show the feasible region. Now, currently you will notice the type of graph is one where we have y equals. We need to change this to an inequality version. So, if we change the type, matching the inequalities we have in the question, we have y is greater than or equal to x squared plus 2x subtract 3. Now, for the next inequality, where we've got y being less than x plus 3, another way which we can input this function in, if we have a graph of the form y equals, let's key in x plus 3. If I press the tools key on this, and then the second option for change symbol, we can change the symbol directly, as so. We have y being less than x plus 3. For the next one, we've got x is less than 1. So, we change the type and match with the inequality. We've got x is less than 1. For the next one, we've got x is greater than or equal to 2. If we go to the type and change this to where we have x equals, we could input here x equals negative 2. And if I press the tools key, the second option, and then the fourth option, we have x is greater than or equal to negative 2. Let's draw the graph. The x minimum will set to be negative 5. The x maximum will set to be 5. X scale will leave us 1. Y minimum will set that to be negative 8. Y maximum will set that to be 8. The y scale will leave us 1. Let's draw the graph. We have the following. Now, we want to show the region which satisfies all those inequalities. If I press the settings key and the fourth option, currently the inequality region type, that's set at union. If we set it to intersection and then draw the graph, here is our feasible region R. And you can also see where we've got dashed lines, those represent strong inequalities, and where we've got solid lines, those represent weak inequalities. We can define vectors using our calculator. If we press the right tab key to enter into the vector tab, we've got vector A, B, C, D, etc., which we can define. Now, if we press the tools key, we can define vector A, which is highlighted in black. So pressing the tools key, we can first of all enter the dimensions. We could have, for example, a 3 by 1 vector. And so we can define vector A to be, for example, 2, negative 5, 7. Let's press the back key. Vector A has now been defined. Now, if I click back onto vector A, I can change, for example, the 7 to an 8. And if I press execute, the vector A has now been changed. If we go back to the calculation tab, we can load up that vector. If we press the catalog key, then scroll down to the fifth option where we have vector. The first option allows us to enter in a particular vector. So for example, we can define vector A, we press alpha, and then this key, vector A, if I press execute, is indeed 2, negative 5, 8. We are given the vector A, which is equal to 4, negative 1, 3, and the vector B, which is equal to negative 5, negative 2, 4. We have to work out 2A subtract 3B. Let's press the tab key to go to the vector tab, and we need to define vector A. So if I press the tools key and then enter in the dimensions, we have a 3 by 1 matrix. So we have 4, -1, 3. Let's now define vector B. We press the tools key. The dimensions would be a 3 by 1 matrix. We have -5, -2, 4. We will now use these calculations. If I press the Tab key to return back to the calculation menu, having defined vector A and vector B, let's input the calculation. We have 2 times the vector A, so we have 2, and to load up vector A, we press the catalog key, the 5th option for vector, the 1st option for vector, and then we key in A. We have twice vector A, subtract 3 times the vector B. So again, we press catalog, the 5th option for vector, the 1st option allows us to input vector B. Twice vector A subtract 3 times the vector B. That is given by 23, 4, -6. We are given the vector A, which is equal to 4, 0, -3. We have to work out the magnitude of A. Let's go to the Vector tab and define vector A. It is a 3 by 1 matrix. We have 4, 0, -3. Let us press this key to go back to the calculation tab. To find the magnitude of vector A, if we press the catalog key, then the 5th option for vector, then scroll down to vector norm. We want the norm of vector A. So let's input in vector A. You will find that to equal 5. We are given the vector A, which is defined as 2, -1, 2. We have to work out the unit vector of A. Let's press this key to go to the Vector tab, and let us define vector A. It is a 3 by 1 matrix. We have 2, -1, 2. Let's return to the calculation tab. To find the unit vector of A, press the catalog key, the 5th option for vector, then the 5th option for unit vector. We want to work out the unit vector of A. And working this out, we have 2/3, -1/3, 2/3. We are given the vector A, which is equal to 4, -5, 1, and the vector B, which is equal to -2, 1, 3. We have to work out A dot B. Let's go to the Vector tab to define the vector A. If we define vector A, we have a 3 by 1 matrix. The vector A is equal to 4, -5, 1. Let us define vector B. That is a 3 by 1 matrix, which is equal to -2, 1, 3. Let's return to the Calculation tab. For us to work out the dot product, let's go to the catalogue, the fifth option for vector, then the second option for dot product. We want to work out the dot product of vector A and vector B. Working this out, we get -10. We are given the vector A, which is equal to 1, 0, 0, and the vector B, which is equal to 1/2 √3/2, 0. We have to work out the angle between vector A and vector B. Let us define vector A. We have a 3 by 1 matrix, which is equal to 1, 0, 0. Let us define vector B. We have a 3 by 1 matrix. The vector B is equal to 1/2 √3/2, 0. Let's return to the Calculation tab. To work out the angle between vector A and vector B, we press the catalogue key, the fifth option for vector, then the fourth option for two-vector angle. We want to work out the angle between vector A and vector B, and working this out, we get pi/3 radians. We are given the vector A, which is equal to -3 to -1, and we are given the vector B, which is equal to 4, -1, 5. We have to work out A cross B. Let us define vector A. We have a 3 by 1 matrix, which is equal to -3 to -1. Let us define vector B. We have a 3 by 1 matrix, which is equal to 4, -1, 5. Let's return to the Calculation tab. Then for us to work out A cross B, let's go to the catalogue, the fifth option for vector, third option for cross product. We want to work out the cross product of vector A and vector B. Working this out, we get 9, 11, -5. We can define a matrix using our calculator. If we press the tab key to reach the Matrix tab, you can see here we can define matrix A, B, C, D, etc. Let's define matrix A. If I press the Tools key, we can enter in the dimensions of a particular matrix. For example, we could have a 3 by 2 matrix, such as the one we see here. And we can fill in these elements. So for example, we could have 8, -5, 2, 7, 0, 6. If I press the back key and then return to the calculation tab, we can then load up matrix A. So if I press the catalog key and scroll down to the matrix option, the first option allows us to enter in a particular matrix. So we want to enter in matrix A. So we press alpha followed by this key. Here you can see matrix A. And if I go back to the matrix tab, and if I press the tools key, and then work my way through to define this matrix, we can edit a particular element. So for example, for this element, I want to have 1 instead. And if I return back to the calculation tab, let's see what our matrix A is now. We have 8, negative 5, 2, 1, 0, 6. We can use our calculator to determine the size of a matrix. Now, if we press the tab key to go to the matrix tab, let's define matrix A. Let's suppose it has dimensions 3 rows and 2 columns. Let's enter in 7, 3, 0, 8, negative 1, 5. Let's return back to the calculation screen. If I press the catalog key and go to the matrix option, we can scroll down to where we have dimensions. I want the dimension of matrix A, so we can input matrix A using catalog. Go to matrix. The first one allows us to input matrix A. The dimensions of matrix A, you can see we have 3 rows, 2 columns. Let's confirm that. Let's show matrix A. Indeed, we have 3 rows, 2 columns. We are given the matrix A, which is equal to 1, negative 4, 2, negative 3, 4, 4, 8, 0, 2, and the matrix B, which is equal to 5, negative 1, 2, 5, 0, 6, negative 3, negative 2, 3. We have to work out 2A plus 3B. Let us go to the matrix tab and define matrix A. It is a 3 by 3 matrix. We have 1, negative 4, 2, negative 3, 4, 4, 8, 0, 2. Let us define matrix B. That is a 3 by 3 matrix. The matrix B is equal to 5, negative 1, 2, 5, 0, 6, negative 3, negative 2, 3. Let's return back to the calculation tab. We have 2 multiplied by the matrix A plus 3 times by the matrix B. Working this out, you'll find the result to equal 17, negative 11, 10, 9, 8, 26, 7, negative 6, 13. We can create an identity matrix of size m times m. If I press the catalog key and go to the matrix option, and then the fifth option allows us to create this matrix. Now, if we enter 1, that creates a 1 by 1 matrix of the identity matrix as shown. If we repeat this process, but this time put 2, this creates a 2 by 2 identity matrix, such as the one we see here. We see along the leading diagonal we have 1s and elsewhere we have 0s. Let's change this to 3. You can see this time we have a 3 by 3 matrix with 1s along the leading diagonal and 0 elsewhere. Let's change this to a 4. You can see we have a 4 by 4 identity matrix with 1s along the leading diagonal and 0 elsewhere. Let's define matrix A. If we press the tab key to go to the matrix tab, and then press the tools key on matrix A, let's define matrix A to have 3 rows and 3 columns. Enter in the elements of matrix A. We could have 4, negative 1, 7, 2, 4, negative 8, 0, 5, negative 7. Let's return back to the calculation tab. We can use the identity matrix in calculations. For example, we could have 5 multiplied by the matrix A subtract twice the identity matrix. So if I press the catalog key, go to the matrix option, and then the fifth option allows us to create an identity matrix. Remember, matrix A is a 3 by 3 matrix, so the identity matrix here has to be a 3 by 3. So we enter in 3, and working this out, you can see the result on the screen. We are given the matrix A, which is equal to 4, negative 1, 7, 2, 4, negative 8, 0, 5, negative 7. We are given the matrix B, which is equal to 8, 1, 1, negative 4, 5, negative 3, 2, 0, 6. We have to work out A multiplied by B. Let's go to the matrix tab. Let's define matrix A. It is a 3 by 3 matrix. We have 4, negative 1, 7, 2, 4, negative 8, 0, 5, negative 7. Let us define matrix B. It is a 3 by 3 matrix. It is equal to 8, 1, 1, negative 4, 5, negative 3, 2, 0, 6. Let's return back to the Calculation tab. We have matrix A multiplied by matrix B. And executing this calculation, we see the result is equal to 50, negative 1, 49, negative 16, 22, negative 58, negative 34, 25, negative 57. We are given the matrix A, which is equal to negative 1, 2, 0, 2, negative 4, negative 6, 5, 2, 1. We have to work out the determinant of A. Let's go to the Matrix tab. Let's define the matrix A, which is a 3 by 3 matrix. We have negative 1, 2, 0, 2, negative 4, negative 6, 5, 2, 1. Let's return back to the calculation screen. If we go to the catalog, then to the matrix option, and then the third option for determinant, we want to work out the determinant of matrix A. We end up with negative 72. We are given the matrix A, which is equal to negative 1, 3, 5, 4, 1, 0, 6, 2, negative 1. We have to work out the transpose of the matrix A. Let's go to the Matrix tab. Let us define matrix A. It is a 3 by 3 matrix, which is equal to negative 1, 3, 5, 4, 1, 0, 6, 2, negative 1. Let's return back to the Calculation tab. If we press the Catalog key, then go to the 6th option for Matrix. We want the 4th option for Matrix Transpose. We want to transpose Matrix A. So let's input Matrix A. You will find that to equal negative 1, 4, 6, 3, 1, 2, 5, 0, negative 1. We are given the matrix A, which is equal to 2, 1, 0, 1, 2, 1, 0, 1, 2. We have to work out the inverse of matrix A. Let us go to the Matrix tab. Let us define matrix A. It is a 3 by 3 matrix, which is equal to 2, 1, 0, 1, 2, 1, 0, 1, 2. Let us return back to the Calculation tab. If we press the Catalog key, then go to the 6th option for Matrix. We want the 2nd option for Inverse Matrix. We want the matrix A. So let us enter in matrix A. The inverse of this is equal to 3/4, negative 1/2, 1/4, negative 1/2, 1, negative 1/2, 1/4, negative 1/2, 3/4. We can draw equations of lines using the 3D graph application. Let's enter into it. Once we enter into it, we see this screen here. And if we press the Tools key, this pop-up appears. If we press the first option to enter equation, and then the first option again to go to the preloaded templates, the highlighted option allows us to enter in equations of lines, and we have different forms as shown here. We have to graph the equation of the line x subtract 1 over 4 equals y subtract 2 over negative 1 equals z subtract 3 over 2. That is of this form shown here. We have x naught equaling 1, y naught equaling 2, z naught equaling 3. A is equal to 4, B is equal to negative 1, C is equal to 2. We will set the x minimum to be negative 10, the x maximum to be 10, and the same thing with the y, and the same thing with the z. Let us toggle off the box and draw the graph. Here we have the equation of the line. We have to graph the equation of the line r equals 1, 2, 3 plus t multiplied by 4, negative 1, 2. That's of the form highlighted here. We have the vector r0 equaling 1, 2, 3, the vector v equaling 4, negative 1, 2. Let us execute. We will set the x minimum to be negative 10, x maximum to be 10. The same thing with the y. And the same thing with the z. Let us toggle off the box. Here is the equation of the line. We have to graph the equation of the line that passes through the points A with coordinates 1, 2, 3 and B with coordinates 5, 1, 5. We will use this highlighted option here. We have the first point 1, 2, 3. We have the second point 5, 1, 5. Let us execute. We will set the x minimum to be negative 10, x maximum to be 10. Same thing in the y. The same thing in the z. Let us toggle off the box. Here we have the equation of the line. We have to graph the equation of the line that passes through the point A with coordinates 1, 2, 3 and has direction vector 4i subtract j plus 2k. That is of this form here. We have x naught equaling 1, y naught equaling 2, z naught equaling 3. A is equal to 4, B is equal to negative 1, C is equal to 2. We will set the x minimum to be negative 10, x maximum to be 10. The same thing with the y. The same thing with the z. Let us toggle off the box. Here is the equation of the line. We have to determine the relationship between the lines x subtract 3 over 4 equals y subtract 2 over negative 1 equals z subtract 5 over 3 and x subtract 1 over negative 1 equals y plus 1 over 2 equals z plus 2 over 2. Let's enter both of these lines in. We have x subtract 3 over 4 equals y subtract 2 over negative 1 equals z subtract 5 over 3. Let us enter in the other line. We have x subtract 1 over negative 1, y subtract negative 1 over 2, z subtract negative 2 over 2. Let us change the x minimum to be negative 10, x maximum to be 10. Same thing with the y's. Same thing with the z's. Let us toggle the box off. Here are the two lines. If I press the tools key, if we go to the graph solve, you can see that they intersect at x equals negative 1, 3, 2. We have to determine the relationship between the lines x subtract 1 over 2 equals y subtract 0 over negative 3 equals z plus 2 over 4 and x subtract 5 over 2 equals y plus 6 over negative 3 equals z subtract 3 over 4. Let's enter in these lines. We have x subtract 1 over 2 equals y subtract 0 over negative 3 equals z subtract negative 2 over 4. Let's enter in the next line. We have x subtract 5 over 2 equals y subtract negative 6 over negative 3 equals z subtract 3 over 4. Let us change the x minimum to be negative 10, the x maximum to be 10. Same thing with the z. If we toggle the box off, you can see the two lines. If I press the tools key, then the second option for graph solve, then the third option for relationship, you can see those lines are parallel. We have to determine the relationship between the lines x subtract 1 over 2 equals y subtract 3 over negative 1 equals z subtract 2 over 3 and x subtract 2 over 1 equals y subtract 1 over negative 1 equals z subtract 4 over 4. Let's enter these in. We have x subtract 1 over 2 equals y subtract 3 over negative 1 equals z subtract 2 over 3. Let's enter in the second equation. We have x subtract 2 over 1 equals y subtract 1 over negative 1 equals z subtract 4 over 4. The x minimum, let's set that to be negative 10, and x maximum to be 10. Same thing in the y, same thing in the z. Let's toggle the box off. Here are the two lines. If we press the tools key, then the second option for graph solve, then the third option for relationship, you can see we have lines which are skew. We can graph equations of planes using the 3D graph application. Let's enter into it. Once we enter into it, we see this screen here. If we press the tools key, and then the first option for enter equation, and then the first option, and then the second option for plane, we have predefined templates which we can use to graph equations of planes. We have to graph the equation of the plane negative 26x subtract 24y plus 3z plus 19 equals 0, and this is in scalar form. That is the highlighted form shown here. So we have negative 26x subtract 24y plus 3z plus 19, and if we draw this graph, let's change the x minimum to be negative 100, x maximum to be 100, the y minimum to be negative 100, the y maximum to be 100, the z minimum to be negative 100, the z maximum to be 100. Let's draw this. We see this over here. Now let's get rid of the box by pressing settings and then deselect box. Here is the equation of the plane negative 26x subtract 24y plus 3z plus 19 equals 0. Let us now graph the equation of the plane in vector form. In vector form, the equivalent equation of the plane is given by r equals 2, negative 1, 3 plus s multiplied by negative 3, 3, negative 2 plus t multiplied by negative 3 over 2, 1, negative 5. Let's enter this equation in. So we press the tools key, and that is this second form shown here, which is in vector form. We have 2, negative 1, 3, negative 3, 3, negative 2, negative 3 over 2, 1, negative 5. Let us deselect the first equation of the plane, which was given in Cartesian form. Let's draw the graph. We see this graph here. Let's now go back. We can enter in the equation of the graph that is equivalent to the given two equations this time passing through 3 points. If we press the Tools key, we have a plane that passes through 3 points. We have the point A, which is given as 2, -1, 3, -1, 2, 1, and 1/2, 0, -2. Let us deselect this graph and let's graph. Here we have the equation of the plane that passes through the 3 points 2, -1, 3 and -1, 2, 1 and 1/2, 0, -2. Now let's go back and let us select all of the graphs. When we execute, you will see that all graphs are equivalent. The point of this is to show that equations of planes can be written in different forms. We have to consider the system of equations x plus y plus z subtract 6 equals 0, 2x subtract y plus z subtract 3 equals 0, 3x plus y plus 2z subtract 11 equals 0. We have to determine the consistency of the system of equations and identify the geometric configuration of the planes. If we press the Tools key to enter an equation and select the plane templates, we have something in scalar form. Our first equation is x plus y plus z subtract 6 equals 0. For our next equation, we have 2x subtract y plus z subtract 3 equals 0. For our third equation, we have 3x plus y plus 2z subtract 11 equals 0. We will set the x minimum to be -100, the x maximum to be 100, the same thing in the y direction, and the same thing in the z direction. Let us detoggle the 3D axis and box. You can see we have the system of equations represented as planes. The system of equations is consistent and they meet at a single point. We have to consider the system of equations -3x subtract y plus z plus 2 equals 0, x plus 5y plus 2z subtract 21 equals 0, -4x plus 2y plus 3z subtract 9 equals 0. We have to determine the consistency of the system of equations and identify the geometric configuration of the planes. Let us enter in the equations of the planes. The first equation is given by -3x subtract y plus z plus 2 equals 0. The next plane is given by x plus 5y plus 2z subtract 21 equals 0. The next plane that's given by -4x plus 2y plus 3z subtract 9 equals 0. We will set the x minimum to be negative 100, x maximum to be 100. The same thing in the y direction, and the same thing in the direction. Let us toggle off the 3D axis and the box. Here are the system of equations. We have something which is consistent, the planes form a sheaf, and we have infinitely many solutions. We have to consider the system of equations 2x plus y subtract z subtract 1 equals 0, x subtract y plus z subtract 3 equals 0, x plus 5y subtract 5z subtract 2 equals 0. We have to determine the consistency of the system of equations and identify the geometric configuration of the planes. Let us enter in the equation of the planes in scalar form. For our first equation, we have 2x plus y subtract z subtract 1 equals 0. For the next equation, we have x subtract y plus z subtract 3 equals 0. For the next equation, x plus 5y subtract 5z subtract 2 equals 0. We will set the x minimum to be negative 25, x maximum to be 25, and the same with the y's. Let us toggle off the 3D axis on the box. And let us explore what we see. What you can see is the consistency of the system of equations is inconsistent. The planes form a prism, and we have no solutions. We have to consider the system of equations x plus 2y subtract z subtract 3 equals 0, x plus 2y subtract z plus 5 equals 0, 2x subtract y plus 4z subtract 7 equals 0. We have to determine the consistency of the system of equations and identify the geometric configuration of the planes. Let us enter in each of those equations. We have x plus 2y subtract z subtract 3 equals 0. We have x plus 2y subtract z plus 5 equals 0. We have 2x subtract y plus 4z subtract 7 equals 0. Let us set the x minimum to be negative 25, the maximum to be 25. The same thing in the y, and the same thing in the z. Let us toggle off the 3D axis and box. Here you can see the system of equations. The consistency is inconsistent. At least two planes are parallel. We have no solutions. We have to consider the system of equations 2x subtract 3y plus z subtract 5 equals 0, 4x subtract 6y plus 2z subtract 10 equals 0, negative 6x plus 9y subtract 3z plus 15 equals 0. We have to determine the consistency of the system of equations and identify the geometric configuration of the planes. Let us enter in each of those equations. We have 2x subtract 3y plus z subtract 5 equals 0. We have 4x subtract 6y plus 2z subtract 10 equals 0. We've got negative 6x plus 9y subtract 3z plus 15 equals 0. Let us toggle off the 3D axis on the box. Here are the system of equations. The consistency of the system of equations is consistent. All equations represent the same plane. We have infinitely many solutions. We have to find the intersection point between the line x equals y equals z subtract 2 over negative 1 and x plus y plus z subtract 4 equals 0. Let's enter in these equations. We've got the equation of the line, which is given by x over 1 equals y over 1 equals z subtract 2 over negative 1. We have the equation of the plane given by x plus y plus z subtract 4 equals 0. We will set the x minimum to be negative 20, x maximum to be 20, the same thing in the y, the same thing in the z. Let us toggle off the 3D axis and the box. Let us rotate. You can see the plane and the line. If I press the tools key, the second option for graph solve and the second option for intersection, you can see they intersect at x equals 2, y equals 2, z equals 0. We have to find the line of intersection between the planes x plus y subtract 3z subtract 4 equals 0 and 2x subtract y plus z subtract 8 equals 0. Let's enter these in. We have x plus y subtract 3z subtract 4 equals 0. We have 2x subtract y plus z subtract 8 equals 0. Let us change the x minimum to be negative 20, x maximum to be 20. Same thing in the y. Same thing in the z. If I press the settings key, let's toggle off 3D axis and the box. Let us rotate. Here you can see the two planes. If I press the tools key, the second option for graph solve, then the second option for intersection, you can see the line of intersection between these two planes is given as x equals 4 subtract 2t, y equals negative 7t, z equals negative 3t. Let us enter into the statistics application. That is the highlighted option shown here. Once we enter into it, we see this screen here. You can see we have list 1, list 2, list 3, list 4. We can continue scrolling through them. We have list 5, list 6, list 7, etc. Those go up to list 26. We can enter in data into these lists. For example, we could have 8.1, 9.5, 6.7, 8.7. We can label these lists. For example, we could call list 1 score. Let's key in that. As shown. What we can do with this list, if I press the tools key, we can sort them in ascending order. How many lists? We have one list we wish to sort out. It is list 1. You can see the calculator has sorted these into ascending order. Let us delete this list. If I press the tab key, this pop-up appears. Once we have inputted in data, we can calculate summary statistics. We can draw statistics graphs. We can carry out hypothesis tests. We can work with confidence intervals. Let's press back. We can have multiple lists. For example, in the first list, we've got data 6, 5, 8, 9. In the second list, we have 8, 4, 2, 8. We have multiple data in multiple lists. And now if we go to the setup, you will see this screen here. And what we can do is work with those to calculate various different statistics. Let us return. If I press the tools key, then scroll down to CSV and then press OK. We can save this list in Excel format. We can clear all lists by pressing AC, as shown here. We have to summarize the statistics for the following data. We have 4, 7, 5, 7, 7, 1, 6, 9, 3, 8. Let's input these into our calculator. We have 4, 7, 5, 7, 7, 1, 6, 9, 3, 8. If we press the Tab key, we can calculate summary statistics as highlighted. We will calculate the summary statistics of list 1. Let us execute. You can see we have the following. The mean is equal to 5.7. The sum of all the data is equal to 57. The sum of the squares is equal to 379. The population standard deviation is equal to 2.32, etc. The sample standard deviation is equal to 2.45, etc. We have 10 pieces of data. The minimum value is 1. The lower quartile is 4. The median is 6.5. The upper quartile is 7. The maximum value is 9. The mode is 7. The number of data mode items is 1, and the data mode frequency is 3. In this example, we have to work out the summary statistics for the following data. We have a grouped frequency table. We have the scores and we have the frequencies. In list 1, we will enter in the scores. Those are 4, 7, 2, 8, 5, 9, 6, 1. In list 2, we will enter in the frequency. A score of 4 has a frequency of 6. A score of 7 has a frequency of 5. A score of 2 has a frequency of 1. A score of 8 has a frequency of 2. A score of 5 has a frequency of 2. A score of 9 has a frequency of 7. A score of 6 has a frequency of 5. A score of 1 has a frequency of 3. We have inputted the data into the calculator. If I press the Tab key and then the first option for Calculate Summary Statistics, here we have one variable statistics. We will be finding the statistics of list 1 and the frequency is given in list 2. Let us execute. We have the following. The mean is equal to 5.90, etc. The sum of the x's is equal to 183. The sum of the x squares is equal to 1273. The population standard deviation is equal to 2.49, etc. The sample standard deviation is equal to 2.53, etc. The number of pieces of data we have is 31. The minimum value is 1. The lower quartile is 4. The median is 6. The upper quartile is 8. The maximum value is 9. The mode is 9. The number of data mode items is 1. And the data mode frequency is 7. we have to construct a pie chart for the dataset. We have item A with frequency 8, item B with frequency 11, item C with frequency 12, item D with frequency 5. Let's enter in those frequencies. We have 8, 11, 12, 5. If I press the tab key to the setup tab, we have the following screen. We wish to draw statistics graph. So we press the second option. The type of graph we want is a pie chart, which is the 7th option. The frequency will be from list 1. Here we can display the results as a percentage or put in the actual data. I wish to put in the actual data. Let us execute. Here is the pie chart. The following data represents the height of students in centimeters, and those are given below. We have to represent the data in a histogram. Let us enter in these data. We have 183, 167, 153, 158, 175, 168, 162, 181, 158, 169, 173, 171, 183, 183, 176, 185, 175, 155, 168, 168, 146, 166, 164, 158. We've entered all the data into list 1. If I press the tab key, what we wish to do is draw statistics graph. The type of graph we wish to draw is a histogram, which is the 5th option. The list is given in list 1. If we execute, let us start at 140 and make the width be 10. Let us execute. Here is the histogram. The following data represents the height of students in meters. These data are shown below. We have to represent the data in a box and whisker plot. Let's enter in those data. We have 1.83, 1.67, 1.53, 1.58, 1.75, 1.68, 1.62, 1.81, 1.58, 1.69, 1.73, 1.71, 1.83, 1.83, 1.76, 1.85, 1.75, 1.55, 1.68, 1.68, 1.46, 1.66, 1.64, 1.58. Let's press the setup tab, we wish to draw statistics graph. The type of graph we want is a box plot. Let us show the outliers. Let's execute. Here is a box and whisker plot. If I press the tools key, then the first option for trace, we can find the minimum, the lower quartile, the median, the upper quartile, and the maximum value. We have to draw a box and whisker plot for the test scores for men and women. In list 1, we will enter in data for men. We have 7.02, 6.97, 7.21, 7.03, 2.04, 6.75, 7.25, 7.51. In list 2, we will enter in data for women. We have 6.01, 5.05, 5.87, 7.62, 1.87, 6.66, 7.01, 7.15. Let us go to the setup. We want to draw statistics graph. For the first graph, we want a box plot, and we wish to show the outliers. And notice, for the first box plot, we will use list 1, which is for men. For the second graph, again, we will select box plot. We will use data from list 2. We wish to show the outliers. Here are both box plots. We have data for men and data for women. If I press the tools key and then trace, here we've got the outlier of 2.04, the minimum value of 6.75, the lower quartile to be 6.86, the median to be 7.025, the upper quartile to be 7.23, and the maximum value to be 7.51. We have the outlier for women being 1.87, the minimum being 5.05, the lower quartile being 5.46, the median being 6.335, the upper quartile being 7.08, and the maximum value being 7.62. We have to construct a scatter diagram for the following test scores. We have maths and physics. In list 1, we will input in the scores for maths. We have 9, 13, 6, 18, 11, 4, 15, 10. In list 2, we will enter in test scores for physics. We have 10, 13, 5, 20, 8, 5, 12, 14. If I press the tab key, we wish to draw statistics graph. We want a scatter graph. Along the X, we will have list 1. Along the y, we will have list 2. Here is the scatter graph. We have the x and we have the y. And if we zoom out, we've got the scale with it. We are given data in x and y. Let us enter these for list 1 and list 2 respectively. We have for x 4, 4, 8, 7, 12, 12, 3, 2. For y, we have 13, 12, 19, 23, 33, 37, 10, 4. We have now entered in the data for x and y. For the first part, we have to find the regression line for the following data. Let us press the Tab key to go to the setup. We wish to draw statistics graph. The type of graph we want would be option A, linear regression graph. Let us execute. If I press OK, currently what is selected is something of the form ax plus b. I want the third option, a plus bx. What you can see for a, we have 0.247, etc. What we have for b is 2.86, etc. So the regression line is given by y equals 0.24, etc. plus 2.86, etc. x. For the next part, we are required to find the product moment correlation coefficient for the following data. The PMCC is the value of R, which is 0.978, etc. And notice the mean square error, MSE, is given by 6.65, etc. We can find probabilities using the binomial distribution, and we can do this using the distribution application. We can access this by pressing the 3 key. The type of distribution we want is a binomial distribution. Now, once we enter in, you see this screen here. We can select the type of tail we have, and there are 4 options as shown here. Where we have data, we can have variable statistics or use statistics from a list. We have X, num trial, and the probability. Where we have colour, this allows us to graph binomial distributions and select the colour of the graph. We are given in this example that X is binomially distributed with parameters 10 and 0.4. Let us enter those into our calculator. For the num trial, we have 10. For the probability, we have 0.4. In the first example, we have to calculate the probability that x equals 2. Let's change the tail to be something of the form x equals. We have the probability that x equals 2, so x here is 2. You will find the probability that x equals 2 is equal to 0.120, etc. For the next example, we have to calculate the probability that x is less than or equal to 5. Let's change the tail type. We will use the first option. We have x is less than or equal to 5, so here x is 5. You will find the probability that x is less than or equal to 5 is equal to 0.833, etc. For the third example, we have to calculate the probability that x is greater than or equal to 3. Let's change the tail to the third option. We have x is greater than or equal to 3, so in this case, x is 3. Executing, you will find the probability that x is greater than or equal to 3 is equal to 0.832, etc. For the fourth example, we have to calculate the probability that x is greater than or equal to 1 but less than or equal to 7. Let's change the tail to the second option. The lower is 1, the upper is 7. The probability that x is greater than or equal to 1 but less than or equal to 7 is equal to 0.981, etc. We are given that x is binomially distributed with parameters 10 and 0.625. We have to find the value of x for which the probability of x being less than or equal to x is equal to 0.533. If we press the catalog key and then go to the distribution option and then scroll down to inverse binomial cumulative distribution, we have 0.533 and then we input in our parameters 10 and 0.625. If we press execute, you will find x to equal 6. A die was rolled 12 times and only 1 6 appeared. We have to test at the 5% significance level that the probability of a 6 on this die is less than 1/6. Let's begin by setting up our distribution. We have x which is binomially distributed with parameters 12 and p. We have the null hypothesis, p equals 1/6, and we have the alternate hypothesis, p is less than 1/6. We can calculate the critical value. That's given by the probability that x is less than or equal to 1. To work this out, let's go to the distribution application. We have a binomial. The tail is x is less than or equal to. X in this case is 1. Num trial is 12. P is 1/6. You will find the probability that x is less than or equal to 1 is equal to 0.381, etc. If we compare this with the 5%, this value is greater than 5%, and therefore we do not reject H0. In other words, there is insufficient evidence to suggest the die is biased. A coin is suspected of being biased towards heads. The coin is tossed 15 times and 12 heads are thrown. Test at the 5% significance level if the coin is biased. Let's begin by setting up our distribution. We have x, which is binomially distributed with parameters 15 and p. We have the null hypothesis, p equals 0.5, and the alternate hypothesis, p is greater than 0.5. We can calculate the critical value. This is given by the probability that x is greater than or equal to 12. We can calculate this using the distribution application. We have a binomial distribution. Let's change the tail to the third option. X is 12. The number of trials we have is 15. P is 0.5. You will find that the probability that x is greater than or equal to 12 is equal to 0.0175, etc. And if we compare this with the 5%, we find that this is less than 5%. So we would reject H0. In other words, there is sufficient evidence to suggest the coin is biased. The probability of scoring a 5 on a die is thought to be 0.15. A die was rolled 40 times and a 5 is scored 2 times. Test at the 5% significance level whether there is evidence that the probability of scoring a 5 is different to 0.15. We begin by setting up our binomial distribution. We have x, which is binomially distributed with parameters 40 and p. The null hypothesis, that's given by p equals 0.15, and we have the alternate hypothesis, p does not equal 0.15. We can find the critical value. That's given by the probability that x is less than or equal to 2. We can calculate this using the distribution application. We have a binomial distribution. The tail is as we see here. X is 2. The number of trial we have is 40. P is 0.15. Working this out, we find that the probability that x is less than or equal to 2 is equal to 0.0485, etc. Now what we need to do is compare this to 2.5% because we have a two-tailed test. And what we find is this value is greater than 2.5%. Therefore, we do not reject H0. In other words, there is insufficient evidence to suggest the probability of scoring a 5 is different to 0.15. In this question, we are given that x is binomially distributed with parameters 20 and p. We have the null hypothesis, p equals 0.7, and we have the alternate hypothesis, p is less than 0.7. For the first part, we have to find the critical region for the test using a 10% significance level, and then for the second part, write down the actual significance level. Here we have a one-tailed test. Let's go to the distribution application. Let's select binomial. Here, because we have p is less than 0.7, the tail is as shown here. We will leave x for now as 0. The num trial, we will set that to be 20, and p is 0.7. Let's execute. Let's change the value here to 10% because we are finding the critical region for the test using a 10% significance level. Now, what the calculator does is it rounds up the value and gives us where we accept h0. And you can see that is when we have x being 11. So to be in the region where we reject h0, we have to take one less than this. 1 less than 11 is 10. So the probability that x is less than or equal to 10 is equal to 0.047, etc. And this 0.047, etc. is less than 10%. So we are in the region where we reject h0. So for the critical region, that is when we have x being less than or equal to 10. And for the actual significance level, that is 0.0479, etc. In this question, we are given that x is binomially distributed with parameters 25 and p. We have the null hypothesis, p equals 0.25, and we have the alternate hypothesis, p is greater than 0.25. For the first part, we have to find the critical region for the test using a 10% significance level, and then for the second part, we have to write down the actual significance level. Let us go to the distribution application. We have a binomial distribution. Now, because we have p being greater than 0.25, let's change the tail to the third option where we have x is greater than or equal to. We will leave x as 0 for now. Num trial, that is 25. P, that is 0.25. Let us enter in the 10% significance level here. So we have 0.1. What our calculator does is it gives us the region where we accept h0. And you can see this is clearly bigger than the 10%. So because we have an upper-tailed test, we have to do one more than this, which is 10. And now you can see this value is less than 10%. So the probability that x is greater than or equal to 10 is 0.071, etc. So for the critical region, that is x is greater than or equal to 10. And for the actual significance level, that is 0.0713, etc. In this question, we are given that x is binomially distributed with parameters 50 and p. We have the null hypothesis, p equals 0.3, and the alternate hypothesis, p does not equal 0.3. For the first part, we have to find the critical region for the test using a 10% significance level. Then, we have to write down the actual significance level. Here we have a two-tailed binomial hypothesis test. So let's go to the distribution application. We have a binomial distribution. The way we will approach this question is to deal with the lower tail and the upper tail separately. Now, we need to recognize that we have a 10% significance level with a two-tailed test. So at either end, we have 5%. So let's deal with the lower tail. For the lower tail, we have x is less than or equal to. We will leave x as 0. Num trial, that is 50, and p is 0.3. Let us change this to 5%. Our calculator gives us values where we accept h0. And because we have a lower tail test, we need to subtract 1 from this. 1 less than 10 is 9. And now you can see this value of 0.04, etc. is less than 5%. So the probability that x is less than or equal to 9 is 0.04, etc. Let's now deal with the upper test. If I press the tools key, then the second option for tail, for the upper tail, we need to select the third option. And again, we change this to 5%. Now, our calculator gives us values where we accept H0, and because we are in the upper tail, we need to do one more than this 20, which is 21. And now you can see this 0.04, etc. is less than 5%. So, we have the probability that x is greater than or equal to 21 is 0.0477, etc. So therefore, for the critical region, we have x is less than or equal to 9, or x is greater than or equal to 21. And for the actual significance level, we need to add together the 0.040 with the 0.047. And adding these together, the actual significance level is 0.088, etc. We can find probabilities using the normal distribution. If we go to the distribution application, and then the second option for normal distribution, we see this screen here. Now, we can select the type of tail we want. So we've got x is less than or equal to. We've got x is greater than or equal to a particular value, but less than or equal to another particular value. We also have x is greater than or equal to. We can have variable statistics, or we can input data in from lists. We can display z values. Here is where we input a particular x value. We have the population mean and the population standard deviation. We are given that x is normally distributed with parameters 20 and 5 squared. This means the mean is 20 and the standard deviation is 5. So let's enter in those into the calculator. We have 20 for the mean and 5 for the standard deviation. In the first example, we have to calculate the probability that x is less than 10. Now, if we take a look at the tail, here we have x is less than or equal to. We don't have to worry so much about the equals to symbol when doing normal distribution calculations. X here is 10. And if we execute, you will see the probability that x is less than or equal to 10 is equal to 0.227, etc. In the next example, we have to calculate the probability that x is greater than 25. Now, if we press Tools, and then the second option for tail, we can change the tail type. We want the third option, where we have x is greater than or equal to. So here we have x is greater than 25. You will find that to equal 0.158, etc. In the next example, we have to calculate the probability that x is greater than 14 but less than 27. So we need to change the tail to the second option shown here. We have 14 for the lower limit and 27 for the upper limit. You will find that the probability that x is greater than 14 but less than 27 is equal to 0.804, etc. We are given that x is normally distributed with parameters mu and sigma squared. We are given that the probability that x is less than 20 is equal to 0.3 and the probability that x is greater than 50 is equal to 0.2. We have to find the value of mu and the value of sigma. Let's go to the distribution application and then select normal distribution. The first thing we need to do is use the option to display z values. We have the probability that x is less than 20, so we use the tail shown here. For now, we will leave x to be 0, mu to be 0, and sigma to be 1. If we execute, the calculator presets for us values shown here. Now, we need to adjust the value of 0.5 to be 0.3. And what our calculator does is it automatically tells us the z value. If I press the tools key and the first option, we can view the value of z. So we have the probability that z is less than negative 0.524, etc. equals 0.3. In other words, z is equal to negative 0.524, etc. We can now use z equals x minus mu over sigma. We have negative 0.524, etc. equals 20 subtract mu over sigma, and if we rearrange this, we have mu minus 0.524, etc. sigma equals 20. Let us now do a similar process with the probability that x is greater than 50 equals 0.2. Let's go back. This time, let us change the tail to match the one we have in the question. Here we will set x to be 0, mu is 0, and sigma is 1. Let's execute. We change this 0.5 to 0.2. Our calculator has found for us a z value. If I press the tools key and the first option, we can see the value of z here. So we have the probability that z is greater than 0.841, etc. is equal to 0.2. In other words, z is equal to 0.841, etc. We can now use z equals x minus mu over sigma. We have 0.841, etc. equals 50 minus mu over sigma, and therefore, rearranging, we have mu plus 0.841, etc. equals 50. To summarize, we have mu minus 0.524, etc. sigma equals 20, and mu plus 0.841, etc. sigma equals 50. We can now solve these two equations simultaneously to find the value of mu and sigma. Let's press the home key and let us go to the equation application. We have a simultaneous equation with two unknowns. We have 1 mu subtract 0.5244005127 equals 20. We have 1 mu plus 0.841 621 2336 equals 50. We have mu equaling 31.51, etc. We have sigma equaling 21.96, etc. So, to three significant figures, mu is 31.5 and sigma is 22.0. We are given that x is normally distributed with parameters 35 and 6 squared. Let us input this into our calculator. Let's go to the distribution application and select the second option for normal. For mu, we have 35, and for sigma, we have 6. For the first part of the question, we have to find the value of x such that the probability that x is less than x is equal to 0.3. Let's make sure that the tail matches up with what we have in the question, which you can see it does. For now, we will leave x as 0. Executing, and then changing the probability to equal 0.3, you can see the value of x shown here. To three significant figures, x is equal to 31.9, i.e. the probability that x is less than 31.853, etc. is equal to 0.3. Now, for the second part of the question, we have to find the value of x such that the probability that x is greater than x is equal to 0.6. Let's go back. Let us change the tail to match what we have in the question. Now, let us execute. Let us change the probability to equal 0.6. You can see the value of x is given as 33.5 to three significant figures. In other words, the probability that x is greater than 33.479, etc. is equal to 0.6. A certain company sells fruit juice in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3 milliliters. The company claims that the mean amount of juice per carton, mu, is 60 milliliters. A trading inspector has received complaints that the company is overstating the mean amount of juice per carton, and he wishes to investigate this complaint. The trading inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1 milliliters. Using a 5% level of significance and stating your hypothesis clearly, test whether or not there is evidence to uphold this complaint. We have the null hypothesis H0 where mu equals 60, and we have the alternate hypothesis H1 where mu is less than 60. We have x which follows a normal distribution with parameters 60 and 3 squared. Therefore, x bar would follow a normal distribution with parameters 60 and 3 squared over 16. We wish to calculate the probability that x bar is less than 59.1. Let's go to the statistics application, then press the tab key, then the third option for hypothesis test. We have a one sample z-test, and we will select data from variable. We have a one-tailed test. Select the second option. We know that mu is 60. We know that sigma is 3. And we know we have the mean being 59.1. And we have a sample of 16. executing, we see that the probability that x bar is less than 59.1 is equal to 0.1150, etc. So if we graph this, then press Tools, and the second option to calculate the p-value, we see that p is equal to 0.1150, etc. If we compare this to the 5%, we see that 0.1150, etc. is greater than 5%, therefore there is insufficient evidence to reject H0 and conclude that the mean amount of juice in the whole population is less than 60 milliliters. A yogurt manufacturer sells 150 gram pots. The amount of yogurt in a pot is normally distributed with a known standard deviation of 6 grams. The company claims the mean fill, mu, is 150 grams. A consumer group suspects the company is understating the mean. They take a random sample of 36 pots and find the sample mean is 152 grams. Using a 5% level of significance and stating your hypotheses clearly, test whether there is evidence to support the consumer group's suspicion. We have the null hypothesis H0 where mu equals 150, and we have the alternate hypothesis H1 where mu is greater than 150. We have x which follows a normal distribution with parameters 150 and 6 squared, and therefore x bar would follow a normal distribution with parameters 150 and 6 squared over 36. We wish to calculate the probability that x bar is greater than 152. If we go to the statistics application, then press the tab key to set up, then the third option for hypothesis test, we have a one sample Z test. We will select data from variable, and we have a one-tail test. We know that we have mu being 150, sigma is 6, x bar is 152, n is 36. And if we execute, you see that p is equal to 0.227, etc. And if we graph, press the Tools key and calculate p-value, you can see we have the probability that x bar is greater than 152 equals 0.0227, etc. Now, let's compare the 0.0227, etc. with the 5%. We see that 0.0227, etc. is less than 5%. Therefore, there is sufficient evidence to reject H0 and conclude that the true mean fill exceeds 150 grams. The diameters of circular cardboard drink mats produced by a certain machine are normally distributed with a mean of 9 cm and a standard deviation of 0.15 cm. After the machine is serviced, a random sample of 30 mats is selected and their diameters are measured to see if the mean diameter has altered. The mean of the sample was 8.95 cm. Test at the 5% level whether there is significant evidence of a change in the mean diameter of mats produced by the machine. We have the null hypothesis H0 where mu equals 9 and the alternate hypothesis H1 where mu does not equal 9. We have x which is normally distributed with parameters 9 and 0.15 squared, and therefore x bar will be normally distributed with parameters 9 and 0.15 squared over 30. We need to calculate the probability that x bar is less than 8.95. If we go to the statistics application, then setup, then hypothesis test, we have a one sample Z test. Data will be selected from variable, we have a two-tailed test. We have mu being 9, sigma being 0.15, x bar being 8.95, n being 30. You will find p to equal 0.0678, etc. If we graph and then calculate the p-value, we see we have 0.0678, etc. So the probability that x bar is less than 8.95 is equal to 0.067, etc. If we compare the 0.0678, etc. with the 5%, we see that the 0.0678, etc. is greater than 5%. Therefore, there is insufficient evidence to reject H0 and conclude that the mean diameter of mats produced by the machine has changed from 9 cm. We can find probabilities using the Poisson distribution. If we go to the distribution application, then Poisson, you see this screen here. We can select the type of tail. The data we enter can be variable or from a list. We can enter in a particular x value, and we have the mean. We are given that x follows a Poisson distribution with mean 2.5. Let's enter this in. In the first example, we have to calculate the probability that x equals 2. Let us change the tail to x equals. We have x equaling 2. You can see the probability that x equals 2 is equal to 0.2565, etc. For the next example, we have to calculate the probability that x is less than or equal to 5. If I press the tools key, then the second option for tail, we can select the appropriate tail. We have the probability that x is less than or equal to 5, which is equal to 0.9579, etc. For the third example, we have to calculate the probability that x is greater than or equal to 3. Let's press Tools and change the tail to the one we see here. We have the probability that x is greater than or equal to 3, and that's equal to 0.4561, etc. For the fourth example, we have to calculate the probability that x is greater than or equal to 1, but less than or equal to 4. Let us change the tail to the one we see here. Our lower limit is 1. Our upper limit is 4. You will find the probability that x is greater than or equal to 1, but less than or equal to 4 is equal to 0.8090, etc. Accidents used to occur at a certain road junction at the rate of 6 per month. The residents petitioned for traffic lights. In the month after the lights were installed, there was only one accident. Test, at the 5% level of significance, whether there is evidence that the lights have reduced the rate of accidents. If we assume H0 to be true, we have x which follows a Poisson distribution with mean 6. We have the null hypothesis H0, where lambda equals 6, and we have the alternate hypothesis H1, where lambda is less than 6. We can find our critical value, that is when the probability that x is less than or equal to 1. We can find this using the distribution application. We have a Poisson distribution, x is 1, lambda is 6. The probability that x is less than or equal to 1 is equal to 0.01735, etc. This is less than 5%, therefore we reject H0, i.e. there is sufficient evidence to suggest that lights have reduced the number of accidents. On a stretch of road, accidents occur at a rate of 0.8 per month. In the month following new markings on the road, it is found there are 3 accidents. Test at the 5% level of significance whether there is evidence to suggest an increase in the rate of accidents along this stretch of road. Assuming H0 is true, we have x which follows a Poisson distribution with mean 0.8. We have the null hypothesis, lambda equals 0.8, and we have the alternate hypothesis H1 where lambda is greater than 0.8. We have the critical value that's given by the probability that x is greater than or equal to 3. We can find out what this is using the distribution application. We have a Poisson distribution. Let's select the appropriate tail. X is equal to 3 and lambda is equal to 0.8. You will find the probability that x is greater than or equal to 3 is equal to 0.0474, etc. If we compare this to 5%, we see this value is less than 5%, therefore we reject H0, i.e. there is sufficient evidence to suggest an increase in the rate of accidents along this stretch of road. Over a long period of time, Fatima found that the bus taking her to school was late at a rate of 2.5 times per month. In the month following the start of the new summer bus schedules, Fatima finds that her bus is late 6 times. Assuming that the number of times the bus is late each month has a Poisson distribution, test at the 2% level of significance whether or not the new schedules changed the frequency with which the bus is late. Assuming H0 to be true, we have x which follows a Poisson distribution with mean 2.5. We have the null hypothesis lambda equals 2.5, and for the alternate hypothesis H1, because we have a two-tailed test, lambda does not equal 2.5. For our critical value, that is the probability that x is greater than or equal to 6. We can find this using the distribution application. We have a Poisson distribution. Let us match the tail as we have in the solution. We have x which is 6 and lambda which is 2.5. You will find the probability that x is greater than or equal to 6 is equal to 0.04202, etc. Now, this is greater than 1%. Remember, we have a two-tailed test, so we have to halve the 2% level of significance. Therefore, we do not reject H0, i.e. there is insufficient evidence to suggest that the new schedules have not changed the frequency with which the bus is late. We can find probabilities using the geometric distribution. We can do this using the distribution application. Entering into it, here we have the geometric distribution. We can select the tail. We can use data from a list or use variable data. Here is where we input a particular x value. Here is where we input the probability. We are given that x follows a geometric distribution with p equaling 0.15. Let's enter this into the calculator. We have p, which is equal to 0.15. In the first example, we have to calculate the probability that x equals 2. So let us change the tail type accordingly. We have the probability that x equals 2. You can see the probability that x equals 2 is equal to 0.1275. In the next example, we have to calculate the probability that x is less than or equal to 5. Let's press Tools, the second option for tail, and let's select the appropriate tail. We have the probability that x is less than or equal to 5, which is equal to 0.5562, etc. In the third example, we have to calculate the probability that x is greater than or equal to 3. Let us change the tail. We have the probability that x is greater than or equal to 3, which is equal to 0.7225. In the fourth example, we have to calculate the probability that x is greater than or equal to 1, but less than or equal to 4. Let us change the tail type. We have the probability that x is greater than or equal to 1, but less than or equal to 4. You will find this to equal 0.4779, etc. A company claims that 1 in 8 of their packets of crisps contain a prize ticket. Lee decides to test this claim, and he buys a packet of crisps each day until he finds a prize ticket. Lee finds a prize ticket for the first time on the 24th day. Test at the 5% significance level whether there is any evidence to suggest that the company is overstating the proportion of packets containing a prize ticket. Assuming H0 to be true, we have x which follows a geometric distribution with parameter 1/8. We have the null hypothesis, H0, where p equals 1/8, and we have the alternate hypothesis, H1, where p is less than 1/8. We can find the critical value, that is, the probability that x is greater than or equal to 24. We can find this using the distribution application. We have a geometric distribution. Let's select the correct tail. X is 24, p is 1/8. The probability that x is greater than or equal to 24 is equal to 0.0463, etc. If we compare this to the 5%, we see this value is less than 5%. Therefore, we reject H0, i.e., there is sufficient evidence to conclude that the company is overstating the proportion of packets containing a prize ticket. An electronics company makes small components for use in computers. It claims that the percentage of defective components coming off the production line is 0.05%. The electronics company sells the components to a retailer. The retailer suspects that the percentage defective stated by the electronics company should be higher. From a very large consignment recently purchased, The retailer tests the components until he finds a defective component. He finds a defective component on the 90th component that he tests. Is there any evidence to suggest that the retailer's suspicions are correct? Test at the 5% level of significance. Assuming H0 to be true, we have x which follows a geometric distribution with parameter 0.0005. In other words, that is referring to the 0.05%. We have the null hypothesis H0 where p equals 0.0005 and the alternate hypothesis H1 where we have p is greater than 0.0005. We can find our critical value. That is given by the probability that x is less than or equal to 90. We can find this using the distribution application. We have a geometric distribution. Here is the appropriate tail. X is 90. P is 0.0005. If we execute, probability that x is less than or equal to 90 is 0.0440, etc. If we compare this to the 5%, we see that this is less than 5%. Therefore, we reject H0, i.e. there is sufficient evidence to conclude that the retailer's suspicions are correct, i.e. the percentage defective is greater than 0.05%. We can work with chi-squared distributions using our calculator. If we go to the distribution application and then scroll to the chi-squared distribution, we can select the appropriate tail. Typically, we would use the third tail. That's because the values are cumulative. When we look at the statistical tables, the values in those statistical tables are those which a random variable with the chi-squared distribution on v degrees of freedom exceed with the probability shown in those tables. So we normally use this. We can select data from a variable or a list. Here is where we input x. Here is where we've got the degrees of freedom. In the first example, we have to find the critical value of the chi-squared distribution with 3 degrees of freedom and a 95% level of significance. We leave the tail as shown here. We have 3 degrees of freedom. We will leave x as 0 for now. Let's execute. Then we change this to 95%. You will find the critical value to be 0.3518. In the next example, we have the chi-squared distribution, this time with 4 degrees of freedom and a 10% level of significance. We have 4 degrees of freedom. Let's execute, and we've got a 10% level of significance. You will find the critical value to equal 7.7794. The random variable x has a chi-squared distribution with 12 degrees of freedom. Let's enter this into our calculator. Let's go to the distribution application. We have a chi-squared with 12 degrees of freedom. For the first part, we have to find the value of x such that the probability that x is greater than x is equal to 0.95. Let us adjust the tail. Let us execute. Let us change the probability to equal 0.95. You will find the critical value to equal 5.226. We now have to find the value of x such that the probability that x is less than x is equal to 0.1. Let us change the tail. We have the probability that x is less than x equals 0.1. You will find x to equal 6.3037. A 5-sided die is rolled 100 times. The results are shown in the table below. We have to carry out a chi-squared goodness of fitness test at the 5% level of significance to investigate whether the die is fair. To begin with, we have our null hypothesis, that is, the die is fair, and that's when the probability equals 0.2. And we have the alternate hypothesis, that is when the dice is not fair, and that's when p does not equal 0.2. We can calculate the expected value of x. That is given by 100 multiplied by 0.2, which is 20. Let us input these into our calculator. If we go to the Statistics application, in list 1, we will enter in the observed values. We have 14, 22, 20, 18, and 26. In list 2, we will enter in the expected values. We have 20 as our expected values. If I now press the Tab key, what we want to do is conduct a hypothesis test. And if I scroll to this option, we can select a chi-squared test. We want a goodness of fit test. The observed values are in list 1. The expected values belong in list 2. Now, for degrees of freedom, we have 5 subtract 1, which is 4. So let's enter this in. And where we have list 3, the calculator will calculate for us the observed minus expected all squared over expected. Let us execute. What you can see is the chi-squared test statistic is equal to 4, and the degrees of freedom is equal to 4. If I press the home key and then go to the distribution application, and if we go to the chi-squared distribution, what we can do is find out the critical value at 5%. So let's select the x is greater than or equal to tail. The degrees of freedom we have is 4. And if we execute, and then if we change this to 0.05, you can see the critical value is given by 9.4877. If we now compare this with the test statistic of 4, we can see this value is greater than 4, therefore we do not reject H0, i.e. there's no evidence that the die is biased. A random sample of 200 American voters were asked about which political party they supported and their attitude to a proposed new form of taxation. The voters' responses are summarized in the table. So we have the attitude, favour, neutral and against, and we have the party, Democratic, Independent, Republican. We have to carry out a chi-squared test at the 1% level of significance to investigate whether there is an association between party supported and attitude to the proposed form of taxation. If we go to the statistics application and then press the tab key and then the third option for hypothesis test, then scroll down, we have a chi-squared test which is a two-way test. The observed values we can enter into matrix A, and the expected values will be calculated and those will go into matrix B. If we begin by entering in the observed values into matrix A, we have 3 rows and we have 3 columns. So entering in the data, we have 58, 16, 16, 25, 4, 11, 17, 20, 33. Let's press back, and let's press back again. Let us execute. So for our solution, let's begin by stating the null hypothesis. That is to say, there is no association between political party supported and attitude to taxation. Then we have the alternate hypothesis, in which there is an association between political party supported and attitude to taxation. You can see the degree of freedom is equal to 4 and the chi-squared test statistic is equal to 30.47, etc. If I go back and then to the expected, and then if I go to the matrix editor and then go to matrix B, here is where we have the matrix of expected values. Now, what we can do is find the critical value at 1%. If I press Home, then Distribution, go to chi-squared, let us change the tail to x is greater than or equal to. We calculated we had 4 degrees of freedom. And we have a 1% level of significance. You can see the critical value is equal to 13.276. If I compare this with the test statistic of 30.47, etc., you can see the 13.276 is less than the 30.47, etc. Therefore, we reject H0, i.e. there is strong evidence of an association between political party supported and attitude to the proposed taxation. We can use our calculator to work with F distributions, and we can do this using the distribution application. Let's enter into it. Let us select F distribution. We can begin by selecting the appropriate tail. We can select data from a list or a variable. We can enter in a particular x value. We have the degrees of freedom. Here is where we have column. Here is where we have rows. And that refers to the statistical tables. We have to find the critical value for the F distribution with 5 degrees of freedom for the column, 8 degrees of freedom for the row, with a probability that exceeds 0.01. We first of all have to change the tail, and we select the third option where we have x is greater than or equal to. The degrees of freedom for the column is 5. The degrees of freedom for the row is 8. If we execute and then change the probability to equal 0.01, you can see the critical value is equal to 6.6318. We have to find the lower and upper 5% critical values for an F distribution with 6 degrees of freedom for the column, 10 degrees of freedom for the row. Let us go to the distribution application. We will select F distribution. For the lower 5%, here is the appropriate tail. The degrees of freedom we have for the column is 6. The degrees of freedom for the rows is 10. We set the probability to equal 5%. You will find that the lower 5% critical value is equal to 0.2463. Now for the upper, if I press Tools and then change the tail to x is greater than or equal to, and then set the probability equal to 0.05, you see the upper 5% critical value is equal to 3.2171. Two samples of sizes 13 and 9 are taken from normal distributions x and y with variances sigma x squared and sigma y squared respectively. The two samples give values sx squared equals 24 and sy squared equals 18 respectively. We have to test at the 5% level the null hypothesis h0 where sigma x squared equals sigma y squared against the alternate hypothesis h1 where sigma x squared is greater than sigma y squared. We have the larger nu, which is equal to 13 subtract 1, which is 12. Then we have the smaller nu, which is equal to 9 subtract 1, which is equal to 8. We have s larger squared equals 24 and s smaller squared equals 18. We can find the critical value at 5% with 12 degrees of freedom for the column and 8 degrees of freedom for the row. We can do this using the distribution application. We have an F distribution. Let's change the tail. We have 12 and 8 for our degrees of freedom. We have the critical value equaling 3.2839. We now need to find the test statistic. If we go to the statistics application, then go to setup, then the third option for hypothesis test, let us select the test to be a 2-sample F test. The data will be selected with variable. Here we have sigma 1 and we want to test if this is greater than sigma 2. Sx1, that will be given by the larger, so that is the square root of 24, and for n1 that will be 12. For sx2, that's a smaller, so we have the square root of 18 and n2 is equal to 8. Let us execute. You can see f is equal to 1.333. If I press the tab key to go to the graph and then press the tools key, you can also see that here. What we can now do is compare this with the critical value of 3.289, and you will see that the 3.289 is greater than the 1.333, and therefore there is insufficient evidence to reject H0. The two populations have equal variances. Two samples of sizes 7 and 11 are taken from normal distributions x and y with variances sigma x squared and sigma y squared respectively. The two samples give sx squared equals 5 and sy squared equals 25 respectively. Test at the 5% level the null hypothesis H0 where sigma x squared equals sigma y squared against the alternate hypothesis H1 where sigma x squared is less than sigma y squared. We can begin by finding nu larger, which is equal to 11 subtract 1, which is 10. We can now find nu smaller, which is equal to 7 subtract 1, which is equal to 6. We have s larger squared, which is 25, and s smaller squared, which is equal to 5. We can find the critical value at 5% with 10 degrees of freedom in the column and 6 degrees of freedom in the row. We can do this using the distribution application. Then we go down to F distribution. Let's change the tail. We have 10 degrees of freedom for the column, 6 degrees of freedom for the row. We have a probability of 0.05. You will find the critical value to equal 4.0599. If we go to the statistics application, then setup, then the third option for hypothesis test, we have a 2-sample f-test. Data is variable. We are testing sigma 1 being less than sigma 2. We have sx1, which is the larger. So here we have the square root of 25, and n1, that's equal to 11. Sx2, that's a smaller one, so that's the square root of 5. And n2 is 7. You will find the test statistic to equal 5. Let's show this on a graph. If I press the tools key, you can see the test statistic is 5. And what we can do is compare this with the critical value of 4.0599. You see 5 is greater than 4.0599. Therefore, there is sufficient evidence to reject H0, so sigma x squared is less than sigma y squared. 2 samples of sizes 11 and 13 are taken from normal distributions x and y with variances sigma x squared and sigma y squared respectively. The 2 samples give values sx squared equals 1.6 and sy squared equals 2.4 respectively. Test at the 10% level the null hypothesis H0 sigma x squared equals sigma y squared against the alternate hypothesis H1 sigma x squared does not equal sigma y squared. We begin by calculating nu larger, which is equal to 13 subtract 1, which is 12. Then we have nu smaller, which is equal to 11 subtract 1, which is equal to 10. We know that s larger squared equals 2.4 and s smaller squared equals 1.6. We can find the critical value at 5%. We have 12 degrees of freedom for the column and 10 degrees of freedom for the row. We can calculate this using the distribution application. We have an F distribution. Let's change the tail. We have 12 degrees of freedom for the column and 10 degrees of freedom for the row. Let's change the probability to equal 5%, and that's because we have a 2-tailed test, so we halve the 10%. You will find the critical value to equal 2.9129. We can now calculate the test statistic. If we go to the statistics application, then hypothesis test, we have a 2-sample f-test. We have data from variable sx1, that is equal to the square root of 2.4, n1, that's equal to 13, sx2, that's equal to the square root of 1.6, n2, that's equal to 11. you can see f is equal to 1.5. And if we graph, then calculate the f value is equal to 1.5. We can now compare this with the critical value. You can see 1.5 is less than 2.9129. Therefore, there is insufficient evidence to reject H0. The two variances are equal. We can work with the t-distribution using the distribution application. Let's enter into it. Let us go down to student t. You will see this screen. Here we can select the tail. Here we can select data from a list of variable. We can enter in a particular x value. Here we have the degrees of freedom. The random variable x has a t-distribution with 10 degrees of freedom. Let us enter this in. We have 10 degrees of freedom. We have to determine values of t for which the probability that x is greater than t is equal to 0.025. Let us change the tail. We will leave x as 0 for now, and if we execute and then change the probability here to 0.025, the probability that x is greater than 2.2281 is equal to 0.025, so t is equal to 2.2281. For the next example, we have to determine values of t for which the probability that x is less than t is equal to 0.95. Let us change the tail. Here we have 0.95. You can see the probability that x is less than 1.8124 is equal to 0.95, so therefore t is equal to 1.8124. A shopkeeper sells jars of jam. The weights of the jars of jam are normally distributed with a mean of 150 grams. A customer complains that the mean weight of 8 jars she had bought was only 147 grams. An estimate for the standard deviation of the weights of the 8 jars of jam calculated from the 8 observations was 2 grams. Test at the 5% significance level whether 147 grams is significantly less than the quoted mean. We have the null hypothesis H0 where mu equals 150 and the alternate hypothesis H1 where mu is less than 150. We have n which is 8, x bar which is 147 and s which is 2. We can calculate the degrees of freedom. 8 subtract 1 is 7. So we have 7 degrees of freedom. We can calculate t with 7 degrees of freedom at a 5% significance level. If we go to the distribution application, then student t, let's match the tail correctly. We have 7 degrees of freedom. And if we change this to 5%, you will find the t value with 7 degrees of freedom is equal to negative 1.894. We can now calculate the test statistic. If we go to the statistics application, then setup, we have a hypothesis test, we have a t-test, we have a one sample t-test. We will use variable data. We have a lower tail test. We have 150, 147, 2, 8, and if we execute, we see the test statistic is equal to negative 4.242, etc. Let's now compare the negative 4.242, etc. with the negative 1.894. We see that negative 4.242, etc. is less than negative 1.894. Therefore, there is sufficient evidence to reject H0 and conclude there is evidence to suggest that the mean weight is less than 150 grams and the customer does not have a cause for complaint. A manufacturer claims that the average lifespan of its light bulbs is 100 hours. An independent testing agency believes that the bulbs may actually last longer on average. A random sample of 15 bulbs is tested, giving a mean lifespan of 103.6 hours with a standard deviation of 5 hours. Using a 5% significance level, test whether there is evidence that the mean lifespan of the bulbs is greater than 100 hours. We have the null hypothesis H0 where mu equals 100 and the alternate hypothesis H1 where mu is greater than 100. We have n which is 15, x bar which is 103.6, s which is 5. The number of degrees of freedom we have is 15 subtract 1 which is 14. We can now calculate the value of t with 14 degrees of freedom. We can do this using the distribution application. We have a student t. Let us select the appropriate tail. We have 14 degrees of freedom. We have 5%. T is equal to 1.7613. We can now work out the test statistics. If we go to the statistics application, then setup, we have a hypothesis test. We have a t-test. We will use variable data. We have an upper-tailed test. We have 100, 103.6, 5, 15, you will find t to equal 2.788, etc. If we compare this 2.788, etc. with the 1.7613, we find that 2.788, etc. is greater than 1.7613. Therefore, there is sufficient evidence to reject H0 and conclude that the bulbs last longer than 100 hours on average. A dietitian claims that a particular diet has no effect on the mean daily protein intake of adults, which is known to be 20 grams under normal conditions. A sample of 9 adults following the diet is taken. The sample mean intake is 18.5 grams with a sample standard deviation of 2.6 grams. At the 5% level of significance, test whether there is evidence that the diet changes the mean daily protein intake. We have the null hypothesis H0 where mu equals 20 and the alternate hypothesis H1 where mu does not equal 20. Here we have a two-tailed test. We have n which is 9, x bar which is 18.5, s which is 2.6. The degree of freedom is equal to 9 subtract 1 which is 8. We can calculate the value of t with 8 degrees of freedom. We can do this using the distribution application. Let's go to student t. Now here for the tail, you can either select the less than or the greater than. it doesn't make a difference because we will be using the mod of this. The degrees of freedom we have is 8. And we changed this to 0.025, which is half of the 5% because we have two tails. You will find that the value of t with 8 degrees of freedom is equal to negative 2.306. Now, of course, if I change this, and then here we have 0.025, we get a positive value of t. So in other words, t is equal to 2.306. Let's now calculate the test statistic. If we go to the statistics application, we have a hypothesis test, we have a t-test, we will select variable data, we have mu, which is 20, we have x bar, which is 18.5, s, which is 2.6, n, which is 9. You will find the test statistic to equal the mod of 1.730, etc. Now, if we compare the mod of 1.730, etc. with the 2.306, you will find the mod of 1.730, etc. is less than 2.306. There is insufficient evidence to reject H0 and conclude that the diet changes mean daily protein intake. The sample mean does not differ significantly from 20 grams. A company introduces a new production method for cutting steel rods. To test whether the new method produces shorter rods on average, 5 rods are cut using both the old and the new method. You may assume that the differences are normally distributed. Using a paired t-test and a 5% significance level, test whether the new method produces shorter rods on average. What we will do to begin with is enter in these data into the calculator. Let's go to the statistics application. Let's enter in the old data. We have 52, 55, 50, 53, 56. Let us enter in the new data into list 2. We have 51, 53, 48, 51, 54. We have the null hypothesis H0 where mu d equals 0, and we have the alternate hypothesis H1 where mu d is less than 0, and we have 5 pieces of data. Now, for us to calculate the test statistic, let us go to list 3, and in list 3 we will work out the differences between these. So, if I press variable, then the 5th option for list, we want to do list 2, subtract, and if we go back to variable, list 1. And if we execute, you see the differences are in list 3. If we go to the setup and then the 3rd option for hypothesis test, we have a t-test, one sample. The tail we have is a lower tail. We will select data from list 3. If we execute, you will see the test statistic is equal to -9. The number of degrees of freedom is equal to 5 subtract 1, which is 4. So now we can calculate the value of t with 4 degrees of freedom. Let's press the home key and go to the distribution application and go to student t. Here we have 4 degrees of freedom. We have 0.05. You will find t with 4 degrees of freedom to equal -2.131. If we now compare the -9 with the -2.131, we see -9 is less than -2.131. Therefore, there is sufficient evidence to reject H0 and conclude that the new method produces shorter rods. A sports scientist wants to test whether a new training program improves sprint performance, i.e. reduces sprint times. 5 athletes run 100 meters before and after completing the program. You may assume that the differences are normally distributed. Using a paired t-test and a 5% significance level, test whether the program reduces sprint times on average. Let us enter in the data into our calculator. Let's go to the statistics application. In list 1, we will enter in data before. We have 13.2, 12.9, 13.6, 14.0, 13.4. In list 2, we have the data after 12.8, 12.5, 13.1, 13.6, 13.0. We have the null hypothesis H0 where mu d equals 0, and we have the alternate hypothesis H1 where mu d is greater than 0. We have 5 pieces of data. We can work out the test statistic. In list 3, we will work out the differences. If I press variable, then the 5th option for list, we want to do list 2 subtract list 1. So we press variable 5 for list and the first option for list 1. You can see in list 3 we have the differences. If we go to the setup and then the third option for hypothesis test, we have a t-test, we have a one sample t-test. We select the appropriate tail. We will calculate data from list 3. You will see that we have the test statistic. Now, of course, we take the magnitude of the -21, which is 21 for our test statistic. We can work out the degree of freedom, that's equal to 5 subtract 1, which is 4. We can now calculate t with 4 degrees of freedom. If we go to the distribution application, we have a student t. Let's select the appropriate tail. We have 4 degrees of freedom. And we have a 5% level of significance. You can see t with 4 degrees of freedom is equal to 2.1318. We can now compare the 21 with the 2.1318. We see that 21 is greater than the 2.1318. Therefore, there is sufficient evidence to reject H0 and conclude that the training program reduces sprint times. A psychologist is investigating the effect of a mindfulness course on participants' stress levels. A random sample of 5 participants had their stress scores measured before and after completing the course. Higher scores indicate greater stress. You may assume that the differences are normally distributed. Using a paired t-test and a 5% significance level, test whether the mindfulness course has an effect on mean stress score. Let us begin by entering in the data into the calculator. Let's go to the statistics application. Here we will enter the before data. We have 28, 31, 27, 30, 29. In list 2, we will enter in the after data. We have 25, 28, 29, 26, 28. We have the null hypothesis H0, where mu d equals 0, and the alternate hypothesis H1, where mu d does not equal 0. Here we have a two-tailed test. We have 5 pieces of data. In list 3, we will work out the differences. We have list 2, subtract list 1. You can see here we have the differences. Let us go to the setup. We have a hypothesis test. We have a t-test, one sample t-test. We have a two-tailed test. We will select data from list 3. And if we execute, you can see the test statistic is equal to -1.685, etc. Now, here we can use the positive version of this or the negative version. It doesn't make too much of a difference because we have a two-tailed test. The number of degrees of freedom we have is 5 subtract 1, which is 4. So let us work out the value of t with 4 degrees of freedom. Let's go to the distribution application. We have a student t, and for the tail, we will use the upper tail. We have 4 degrees of freedom. We look at the top 2.5% because we have a two-tailed test. You can see the value of t is equal to 2.7764. Now, if we compare the 1.685, etc., with the 2.7764, we see that the 1.685, etc., is less than 2.7764. Therefore, there is insufficient evidence to reject H0 and conclude that the mindfulness course changes mean stress scores. Two groups of students, X and Y, were taught by different teachers. At the end of their course, a random sample of students from each class was selected and given a test. The test results out of 50 were as follows. We have the results shown for group X and the results shown for group Y. We have to test at the 10% level of significance whether or not there is a significance difference between the means. Let us begin by entering in the data into our calculator. Let's go to the statistics application. In list 1, we will enter in data for group X. We have 40, 37, 45, 34, 30, 41, 42, 43, 36. In list 2, we will enter in data for group Y. We have 38, 43, 36, 45, 35, 44, 41. We have the null hypothesis H0, where μx equals μy, and we have the alternate hypothesis H1, where μx does not equal μy. If I go to the setup, then hypothesis test, and then t-test, we have a two-sample t-test. We will select data from a list. We have a two-tail test. Let's select on the option for pooled, and if we execute, you can see we have 14 degrees of freedom, and the test statistic is equal to negative 0.719, etc. Let us calculate the value of t with 14 degrees of freedom. If we go to the distribution application, we have a student t. Because we have two tails, let's select the third option. We have 14 degrees of freedom. And because we have 10% in total, that means we have 5% either side. So let's change this to 5%. You can see t is equal to plus minus 1.7613. And that's because we have a two-tailed test. Now, this negative 0.719, etc. is in between negative 1.7613 and 1.76 and 1.7613. Therefore, it's in the acceptance region. So, we do not reject H0. On the evidence given by the two samples, there is no difference between the means of the two groups. The breaking strains of reels of string produced at a certain factory have a standard deviation of 1.5 kilograms. A sample of 100 reels from a certain batch were tested and their mean breaking strain was 5.30 kilograms. Find a 95% confidence interval for the mean breaking strain of string in this batch. We can do this using the statistics application. Let's enter into it. If I go to the setup, then the fourth option for confidence interval, we have a one sample Z interval we will use variable data. We are finding a 95% confidence interval. We have sigma, which is 1.5. We have x bar, which is 5.30. And we have n, which is 100. The 95% confidence interval is given by 5.006, etc., which is less than mu, which is less than 5.593, etc. A sample of 6 trout taken from a fish farm were caught and their lengths in centimeters were measured as follows. Those are shown below. Assuming that the lengths of trout are normally distributed, find a 90% confidence interval for the mean length of trout in the fish farm. We can do this using the statistics application. Let's enter into it. Let us enter in the data. We have 26.8, 26.0, 25.8, 25.5, 24.3, 24.6. Let's go to the setup. We have a confidence interval, and here we have a t confidence interval, a one sample t interval. We will select data from the list we have just created. We want a 90% confidence interval. You can see the 90% confidence interval is given by 24.738, etc., which is less than mu, which is less than 26.261, etc.